many of you plan to stay that way? Don't answer. That was the part that people wouldn't want to see.
I would have been raising my hand a little bit.
The reason I bring that up is because hardware and software is like a marriage, and it's a good metaphor to the way that they have to work together to get a job done, to produce interesting results. Hardware just sits there, software doesn't run, you get them both together, and then stuff starts to happen. Some really cool, interesting, and fun stuff. So then there was the old saying, the old proverb, about the young man who was wondering whether he should get married. And so he loved the girl, he was wondering should he do it, and so he decided he knew how he was going to find the answer. Because he knew of a wise philosopher that lived far away, and he decided he was going to go ask him, and so he went on a long journey over mountains, through rivers, and then he went up into the forest, on top of the hill, to the grass shack where the philosopher lived. And he went inside and he bowed and said, "Oh, philosopher, oh wise guru, please tell me, should I get married?" And the philosopher looked at him and immediately responded, "Of course you should get married, my son." And away the young man went, happy. But then he stopped and he walked back and he went into the hut one more time and he said, "Oh, philosopher, could I please ask one more question? How did you know that I should be married?" And the philosopher said, "Well, my son, that too is an easy thing. If you find a good wife, then you will be happy, and that is a good thing. If you find a bad wife, you will become a philosopher, and that too is a good thing." So there's a few morals there, including be careful who you're asking for the answer and where he's from. But in general, the reason this applies is because this marriage of hardware and software and current hardware trends is in danger, if left unchecked, of turning us all into philosophers. And we'll still be married, but it won't be nearly as much fun. And so part of what I'm going to talk about today is the directions and trends in hardware, and more people are aware of these. You heard it mentioned just already. I'm going to spend a decent chunk of the talk on that motivation, because a lot of it, not just in, yeah, it's happening and why, but understanding what kinds of ways our software will have to be different over the coming 5 years, 10 years, will help to sort of motivate the actual language syntax, which is actually less interesting, although I know that's the reason we're here. So we will get to that as well. Most of the slides are about actual language syntax. But the motivation and context is important too. So let's first talk about truths. And with this first slide, one of the things I want to ask you is how many of you are generally familiar with what this slide is about, just glancing at it? Every time I ask that question, the percentage of hands that goes up is higher. And that is a good thing. It's still not 100%. But basically, for 30 years, we had a wonderful honeymoon. The honeymoon was in the form of the free lunch. You would write a piece of software, and if you were in grad school, it wasn't fast enough, then there was a very easy solution. You go take a sabbatical, then you come back and you run exactly the same binary on new hardware, and now it's fast enough, right? People actually did this and got theses published that way. And the reason that this worked so well for 30 years, and arguably even longer, but in our worlds, let's say 30 years for the microprocessor, was because as you started getting more and more transistors, Moore's law gave you, about every 2 years, double the number of transistors. As you got more and more of them, what these clever, wonderful chip architects did with them is to say, oh, I've got more transistors. I'll find out ways to make your sequential program run faster. And for instance, through the 1980s, pretty much every major chip generation used the extra transistor budget to make the chip more complex with one big feature, maybe pipelining or something else, that would make your single-threaded execution run faster. And there'd be other stuff too. They play with the clock speed, frequency, that's the second dial, and power as well. But they use the extra transistors to speed up your single-threaded execution. Now, you can see where this starts to get diminishing returns. In the 1990s, every major chip generation, typically from about any vendor, would use all those extra transistors to do 3 or 4 or 5 or 6 smaller additions of complexity that would make your single thread of execution run faster. And there are still a few left, but we've got to the point where mining for the gold costs as much as the gold, just about. And we're going to still see some improvements that way, but they're not exponential anymore, they're more marginal and incremental. In particular, also, clock frequency isn't going to scale either because we've pretty much maxed out around 4 gigahertz for now. There'll be some increase still over the next decade, but it'll be modest. It won't be what we're used to. And yet, if you're a hardware vendor, by the way, do any of you work in hardware? A few? Okay, I'll pick on hardware. Oh yes, of course, I should know. Okay, I would ask you to name your affiliation. So, but they work in this building. So, when we go to Mr. Hardware Vendor, we say, oh, Mr. Hardware Vendor, I have a present for you. Every 2 years, I have double the number of transistors. Now, until now, you knew what to do with them. You would make your chip more complex, and my application would run faster. All's goodness. That was till 2002. We're just now waking up to the fact that the world has changed. But that was good up until 2002. So now I come and I say, by the way, here's your boatload of transistors, straight from FedEx. What do you do?
Build a bigger cache.
Okay, you did that too for a while. So you give me more cores.
Right.
So you give me twice as many transistors. Now I get 2 cores because we can't really make one that runs faster. So I get 2 and then 4 and so on. Moore's law is alive and well. Ignore all those /dot threads about Moore's law being dead. It's good till for another maybe decade or so. It'll die eventually. It has to. Nothing exponential can go forever. But for now, we're getting those transistors, and we're just going to get more and more cores. No longer faster processors, but more of them. And in fact, if you want to estimate the number of processors, a very good lower bound is just to go through and follow Moore's law. So in shipping commercial products as of today, here in September 2006, and the curves are similar for Intel and AMD. I'm just picking on Intel data, but everybody, Spark, PowerPC, everybody's affected by this. If you wanted to go out and get a typical desktop PC or even a developer workstation, but I'm talking desktop, not a server, maybe a single socket machine, how many cores can you buy today if you go to Dell or Gateway? How many cores in that machine?
2 in one socket.
Mostly 2? Mostly? Why? Whoever said mostly, why mostly? Was that you?
Well, it's because, well, Sun is selling 4-core, 5-thread chips.
Yeah, so
Sun's more expensive.
Sun's got Niagara and other things going on as well. And in fact, if you go to Dell, you can buy a 4-core machine today because they have 2 sockets. Yeah. So 2 socket machines, but for a single socket, and that's kind of why I said single socket, yeah. Single CPU package, dual core. Okay, so dual core is what we buy today. When is 4-core going to be available?
Well, Woodcrest is 4-core already. Woodcrest is a multi-chip, so they have
Kinsfield, right?
What?
Okay,
Oh,
Woodcrest is a server product.
Kinsfield.
End of year.
End of year, this year, yeah. Right? So if you've been watching the news, you've noticed that Intel, who are going to ship 4-core next year, are shipping it this year. So, you know, your Christmas presents, you can warm up your checkbooks for those new Dell computers. And if you get one of the dual core, the dual socket ones, that'll be 8, should you so choose to have them. And so that's only a few months away. So when do you think that we'll see 8-core per socket?
2 years.
2 years from then, so that would be roughly late 08?
Late 08.
Okay, when would we expect to see 16-core machines?
If you believe Moore's law.
If you believe more, well, we believe. It's an article of faith, at least for 10 years. Okay, so 2010. Okay, so here's the question that will get you a book. And the closest answer, there is no one answer, but what do you think, that's I think a lower bound, what do you think is an upper bound on the maximum number of cores should chip vendors choose to actually build these parts? What do you think is an upper bound on the number of cores that we might see in the 2010 timeframe?
Well, it depends on the client or on the server.
I'm talking, and thank you very much for that. I'm talking purely on the client, not on the server, because server is special. And virtually everything I'm going to talk about in this talk, including the software problems, are purely client side. So thank you for that.
Well, more than 4 hardly makes any sense because there's no software to do anything.
So some people say, well, they won't build it because nobody can use more than 4 anyway. These are the optimists. Did you say you worked for a hardware vendor? You might find that your company's roadmap is different from what you just said. But did anybody pick a number? So we've got somebody who says 60. 64? 64. Okay. Anybody willing to?
65.
Remember, this is the one where you you get the, and of course this is all prognostication, so I'm going to measure you against my purely personal objective or subjective prognostication, but it's not to go over. So, okay, so we got 64.
But isn't there a problem with your limit? That you get diminishing returns, pretty much inverse Moore's law as you start adding cores.
We can talk about some of those performance issues, but just putting cores in a device. So somebody gave me 64, 2010, anybody else?
30.
Okay, so 32, 64, 64, some really wild guys are ready to go out there.
Pipeline to memory starts being a problem.
Yeah, so memory and other issues. I'm not going to talk too much about the hardware, but let's just take a quick look at what we might imagine. So certainly if we just followed Moore's law and we had these big out-of-order cores, these big complex cores that we've been building up till now, because that's what we've been just making them more and more complex, and if we just make more of those, then you can pretty much read off Moore's law what you might expect to see. But here are a couple of other factors to be aware of. There are others, but here are some major ones that I worry about, and we'll see how they all pan out. Clearly that first one, as Moore's law gives us double the transistors, we'll double the cores on a chip, because we'll have to adjust caches as well, but this is forcing us to greater hardware parallelism. There is one other effect, though. Those in-order cores, those simpler ones, from the simpler days when life was simpler, they're more testable. They actually give you just as good floating point throughput as a complex one. They take up a quarter of the die area. They take a fraction of the heat, and power is a big deal. So there's actually some desire on the part of hardware designers across the industry to say, wouldn't it be nice if we could go back to the good old days and just go to a quarter the size in-order cores? I mean, if people are actually writing software that can take advantage of many cores, which is a gating factor we're going to talk about, well, why not? So you might see a one-time 16x jump from getting 4 times as many cores because they're a quarter the size, roughly. And also because I'm going to point out another reason, you're going to need hyperthreads on these cores much more than you do on the out-of-order cores. So when most of you think hyperthreading, you probably think like Intel hyperthreading and 20% performance improvement if you're on a good day. Why care? How many are in that category? Okay, you will care more if we ever go back to in-order cores, because it turns out that having the same chip, the same core, doing several threads of execution in hardware at the same time is going to be very important for the reason that you cited, which is memory, because that is the way that you hide memory latency. So if we go back to in-order cores, there's going to be fewer transistors per core, which also increases hardware parallelism. But then there's this vicious cycle that as you get poorer memory bandwidth per core, well, the way that we always deal with bandwidth is we trade off better bandwidth for worse latency, right? We always do this. That's just the way you deal with bandwidth issues, right? Of course, the more you trade off worse latency, the more hardware threads you have to cover the latency. Because every time you execute an instruction that says, go fetch something from memory, instead of sitting there doing this for 60 cycles, or 100 cycles, or 300 cycles, you can switch to another thread that can actually keep going, and so you hide that latency. That's the reason you want hardware parallelism. All of these things point at this thing in the middle, so a more realistic picture is this one. I noticed that nobody picked 128, but who was the first person to say 64? You, sir, have got a book. Congratulations. Now, I am not claiming, and just grab me afterwards with a pen. I am not claiming that that is actually going to happen, but if you just take a look at what this says, if all we do is use the transistors to make more cores, and they might use it for a few other things, like somebody just bought a graphics processor vendor, so expect to see that on a core. I don't know any more than you do about it, but boy, that's the thing everybody would expect to see. So some of the transistor area will go to things like that. System on a chip is getting more popular in terms of technology and design. But if all you did was make lots of complex cores, you're looking at around this baseline. But if you take the one-time jump, and I'm including a year of lag because there are other architectural things you have to do to go to simpler in-order cores, especially deal with memory and things like that, then expect to see number of cores and number of threads, because number of threads is what really matters, right? If you need to keep 4 threads per core running, which is the typical number even for Niagara, if you keep have to keep 4 threads running to get decent performance out of that core. That means you better have that much parallelism in your application. You don't care about the number of cores, you do care about the number of threads. And I point this out because today you can pretty much ignore hyperthreading. And I believe if you go to Dell's website like I did yesterday and you order a brand new workstation PC, they have an option for turning the hyperthreading on. I think it's off by default. And so if you turn on hyperthreading, you might get in some application workloads a 20% boost. You know, if you're really good, you might get 40. But you know, it's not double for having 2 hardware threads. On in-order cores, it is much closer to linear speed up. So, should chip vendors build something like this? And there were rumors earlier this year about Intel building something very much like exactly those numbers in this time frame, actually, because it was a server part that was rumored. Regardless of rumors like that, if they build these, then, boy, if you're going to get any use out of the chip, the software needs to be more parallel too. And this is a big problem for us.
There was a MIPS licensee that was making a 32-core chip as of at least a year and a half ago. I don't know if anything came of it.
Oh, and MIPS is a good example, by the way. Pull out your cell phone. You are not safe with your cell phone because ARM, MIPS, all the small, the embedded mobile chip vendors are on the same kinds of curves. They just may be a little behind, but it's the same kind of curves. So by the way, there's good news here. We won. Like we, the industry, won. We put a PC on a computer on everybody's desk, in everybody's living room, we're working on that part, in everybody's pocket because you're carrying these cell phones around. And I guarantee you the cell phone you're using today has more capacity and memory and performance than the mainframe you were probably time sharing on 30 years ago. So what's different now? By far, yeah. So maybe 20 years ago for some of us. So what's different now? Now we're at the beginning of an evolution where the next thing, since we conquered that one, you know, at least North America and Europe, now the next thing is let's put a Cray inside everybody's purse, because that's exactly where we're going. And they have to be programmed a different way. So the truth is somewhere in there. I'm not claiming that by 2013 we'll have 512 threaded processors. I do believe it'll be at least 32, and it could be 512. We'll see 2 years from now, 5 years from now, how these things actually work out. The reason I put this slide up is because I think a lot of people think, you know, this might affect me in 10 years. Exponential curves catch up on you real fast. But a big gating factor in whether people actually build this, whether hardware vendors actually build this, is software. They will not build it if nobody's going to buy it because it doesn't run their software any faster. One last note, if you just go back a few slides to the free lunch is over slide. I labeled these for a reason. Montecito is your dual-core Itanium chip, 1.7 billion with a B transistors on one chip. Don't ask me, it just, they do it. Instead of having a dual-core Itanium, using the same transistor budget and a bit of engineering, but I can say that because I'm not a hardware vendor, so I don't have to do the engineering, and a bit of engineering, you could have had over 100 Pentium-class cores and 16 meg of L3 cache all on the same chip, just to give you a sense of just how many transistors we're talking about. So that is manufacturable. You could have had a 100 Pentium core chip today, this year. Why doesn't Intel build it? Because who would buy it? Where's the software that would run on it? And so we have a challenge and an opportunity, as the saying goes, to go through these forces, and as we climb these curves, to end up in a place where we can enable this kind of thing and make our applications better for it. So somebody already said this, I'm not concerned about server applications much. You know, geniuses can already write scalable server applications. It's easy for a server to just go sit in a room and service 1 million requests all day long. They're typically nice independent requests. It's easy to spin up n threads, as many as you've got cores, and service the requests in parallel. And when they ever do step on shared data, it's usually in a structured database. And you know, SQL is such a wonderful place to be because we have 30, 40 years of research into how to do automatic contention and locking on a very highly structured data store with rows and columns, and to automatically escalate row locks to page locks to table locks to do index locks. And what do we tell the programmer to do? The programmer has this wonderful model. It's called transactions. Begin, do whatever I want, end. That is like really nifty and simple. And in fact, what happens if the server detects automatically that two transactions conflict? It just sees, decides who's ugliest, shoots him in the head, starts him over, lets the other one complete, just runs him again, right? And the programmer doesn't have to deal with any of that complexity. It can be all varied because it's highly structured. Typical client apps are nothing like that. Typically, the user pushes a button, and you expect to somehow start something, even if it doesn't return right away, in such a way that it doesn't prevent other foreground processing, that the app stays responsive. Or if you care about the performance, that he pushes a button, and you under the covers have to break this up into 1,000 pieces of work and put it back together again to get faster response. It's not just natural parallelism. Usually not executing the same code n times. When you have shared data, you have pointer chasing graphs in memory that is so far from the nice structured SQL world that it might as well be a different universe. And you have to do all the transactions using explicit locks yourself. There is not a transactional way to deal with this. And then there's some legacy issues that all platforms have. So how do we get people in this world to write hardware that will run, to write programs that will run on that kind of hardware? In particular, how do we get the free lunch back? I want to write, maybe, I assume you do too. I want to write an application, ship it, go away, collect royalties as people keep buying it because it runs faster on next year's hardware, and it runs faster still on next year's hardware. And that's just not the case for applications the way we've always written them anymore. So let's look at a couple of problems in the programming model. When we tell people to write multi-threaded applications, generally the status quo is threads and locks. You got some people who are in OpenMP land for a very narrow place, and they juggle razor blades and they make sure it comes out right, and that's wonderful. There's people in OpenMPI land who do message passing, which is also great. But most people are out in threads and locks land. It's like the Wild West, you know, except with Gatling guns instead of just revolvers. So unstructured free threading is awful because if I just give you a capital T thread, what do? Well, you just say, oh, execute this function. You can just do anything. There's no discipline. There's no abstraction. It's just another function to execute asynchronously. And you'll see what I mean by abstractions as we get later. Now, how do we deal with that? Because I can do anything in there. I can suddenly lock and wait for another thread, but it might be waiting for me, and I suddenly deadlock. How do I prevent those kinds of things? How can I avoid affinity issues where if I do a certain OS call on this thread, I had better do the next OS call that corresponds to it on this same thread, not somewhere else. The obvious example is taking a lock and releasing it. But there are other things that you call in just about any major operating system that gets you thread affinity, and guess what? Most of them aren't documented. So sometimes you need to know what things do I need to do and stay on the same thread. So there are some ways that we deal with this today. Many things we do today is use messages. We might use MPI, we might roll our own messages, so that we use that instead of, say, direct data sharing. We send messages around instead of direct locking so that people can say, hey, here's something. It flies asynchronously. It can still be in memory. And then somebody else, when he wants the result, can wait for it and catch the result and use it. People also use work queues. So instead of having lots of threads running and contending, people will often break their application up into chunks of work in a queue and then spin up the right number of worker threads to fit whatever their current hardware is, and then just have them all pulling stuff off the queue. And then do this by hand. Like, this just cries out for automation. In fact, it is automated partly if you look at .NET background worker and queue user work item. If you look in Java, the executors or executors? No one knows for sure. But tomorrow we would like to have better abstractions. For instance, I'm going to talk about active objects, where function calls just implicitly are messages, and they're at a level that you can reason about the abstraction. Futures is an important one. And it goes along with the advice, like today we don't roll our own vtables like we essentially did when we did OO in C. Well, we're doing concurrency in C. Why do we have to roll our own vtables? We need better abstractions. I can reason about a virtual function much better than about a table of function pointers and doing the offset machinery myself. If you thought that was the biggest problem, boy, we're going to have fun. Because the bigger problem is locks. How many of you feel reasonably comfortable that you can code correctly with locks? I know some people who are not sure whether they should be brave enough to put up their hand, even though they think they know how, right? Just because of the way I phrased that question. Until a few years ago, I thought I knew how to program with locks. I discovered that I actually didn't know how to program with locks. There are a lot of things you have to learn. Probably the most important problem with locks is that I have to go in and do surgery by hand. Get inside the patient and do explicit locks, and I can't really say what data is protected by what lock. I sort of have to remember, and I have to remember to use my locks in a way I can't deadlock. The chief problem is that locks are not composable. Composable software is the foundation for everything we have been doing for the last 20 years. Plugins, object-oriented hierarchies that I can extend with derived types. I can ship you the library, and you can derive from the framework with your own types. All of that composability, libraries for crying out loud, just linking together libraries that were authored separately. The whole world that we know of, that we live in, is built on building small pieces of software into larger pieces, and putting them together. And one important thing to remember, I sometimes give this talk to hardware audiences. It's a real trip, because until a year and a half ago, I never talked to hardware audiences. Now, half of my talking is to hardware audiences. I feel like the lone, cold little emissary from the world of software, you know, with the little hat out saying, can you help, please? Alms, please? One of the things that astonishes hardware people who really, I mean, they're experts in their field, is not their job to be familiar with software. It's the monolithic, the software that runs on top. Never mind how complex the operating system is, how complex the applications are, the runtimes in between. It's just the software, right? One of the things that is a surprise every time that I talk to hardware audiences, I say the following, and I can look and I can see at least 3 or 4 people in the room open their mouths literally with surprise. The statement is this: a lot of times, software is never composed, or is composed for the very first time on the end user's machine. You say, well, how could that be? Didn't you test it before? Well, of course I tested my part. But you download Firefox, you download 2 add-ins, and I'll bet you each add-in has been tested with Firefox, one would hope, before they ship the add-in. But you know, you, lucky sir, might be the first person in the world to ever have downloaded those 2 particular add-ins. And so you get to test whether they work together or not, right? Now, the reason OO is so important and has been such a wonderful tool is because it gives us abstractions that make it easy to compose software, virtual functions, and all sorts of classes, things like that. And this idea that I only need to know about the interface of something and not the implementation to plug them together is a wonderful thing. That's what enables us to do what we do. Locks are not composable. This is the key thing. You cannot take 2 pieces of lock-based code that each uses their own locks eternally, put them together, and even if you can prove that these 2 are correct in isolation, you cannot know that the result is still correct. You can do that for objects. You can't do that for locks. The reason is, here's a very simple example. If you have any code that can take a call from one into the other, or and then some other piece of code can call from this one into the other. If you look at any book on concurrency, and they talk about locks, example number 1 will be, don't call unknown code while holding a lock. Now, why is that true? Why shouldn't you call unknown code while holding a lock? Anyone? Why? It'll deadlock right away if you call unknown code while holding a lock? I did another threat. Right, right. This is the part I didn't really actually think about until 5 years ago. I've been using locks very happily until then, and just didn't happen to stumble into that swamp, or at least not often enough that I could figure out what was going on in the code. So the problem is you hold a lock and you call some unknown code, like a virtual function call, for example. That's the same thing as calling unknown code, because you have no idea what you're going into. The code you call might take a lock, a completely different one that you know nothing about that doesn't affect yours at all. And you're still okay so far. The fun part, the really, really fun part comes when some other thread in the system that starts in this library takes a lock and then calls out into this library, which then tries to take the other lock, its lock, in the other order. And now you're still okay, except for a race. It's a deadlock waiting to happen until they just happen to try to do it at the same time. Enjoy your debugging session. There goes your sunk. This is awful stuff. By the way, the world's best frameworks do this. If you look at the shipping.net sync hash table, which is a wrapper-around hash table which basically is a monitor. It takes a lock unlock on every method call. Well, I hope they're going to fix this in the service pack, because this one you can actually fix. It takes a lock, then on insert, you're going to insert an object into the hash table, right? Takes the lock, calls get hash code, and then inserts it into the table. Get hash code is a virtual function. You have no idea what it's going to do. Now, some of you may be thinking, okay, like, let's get over it. Get hash code. Seems pretty safe. How could get hash code? Why would it ever take a lock? I mean, it's just going to XOR some bits together and maybe rotate it there, right? Like, come on, get real. Oh yeah? So I give you an object I want to put in a hash table that's demand loaded from disk. Oh, and this is the first time as a proxy. So it's the first time you happen to be using that object. So it takes the lock to access the disk. And now you're in this wonderful situation. The fact that locks are not composable is a real Achilles heel. The bad news is we don't have anything better. This is how we deal with objects in memory that are shared and mutable. I'm not going to talk about it much, but you'll hear a lot about lock-free programming, and there are maybe 12 people in the world who ought to write it, and I'm not one of them. So for those who are we're sort of inclined to look into lock-free as a solution, there definitely is a place for it. Some real super rocket scientists, not just journeyman rocket scientists, super rocket scientists will write some libraries that you can use. Like if you look at JSR 166 for the extensions to Java, the lock-free libraries that you don't have to do external locking on, like a hash table and a few others. And .NET is having similar things. And you can then use those and not have to lock on uses of the library, although you still have to lock on simultaneous uses of the objects in those containers, but it makes things easier for you. But lest people get all crazy and think that lock-free is the answer, it's not. I won't even try to describe how hard it is to write lock-free code correctly, but one way to sort of gauge that is to notice that if you, dear sir, if any one of you right now can think of a new lock-free algorithm, go home, write a paper, it's publishable. You will get a refereed paper published if you can find a new lock-free algorithm or a new lock-free data structure. And there are many common data structures, basic ones, for which there are not yet any known lock-free implementations. Just as a note, this is important, but this isn't the answer. So what do we want to do with locks? Well, here are the things I think we should do in order. Now, we can't entirely get rid of locks, but let's start with greatly reducing locks. The most important thing we can do is enable transactional programming styles. That is, that in code I can say atomic brace and then do whatever and brace, just like begin transaction, end transaction. And version memory like I version cells in a database. Easy to describe, hard to implement. Virtually every major software and hardware company on the planet right now has multiple incubation projects in transactional memory, and you will find a rich field of research papers. This was just discovered about 10 years ago, which means that you usually need 10 to 15 years to get into products, so we're on that cycle now. But everybody's investing heavily in this idea of composable atomic blocks because it is the only hope we have to seriously reduce our use of locks. It's the only alternative to locks, the only hope we have for an alternative to locks. The idea is I go into an atomic block and I say x equals 1, y equals 1, read z, brace. And somebody else might be running other atomic blocks. The system can tell when I try to commit whether or not I read or wrote any of the same memory locations as other threads in the system, also in their atomic blocks. And if all I'm doing is touching memory, it could just, for example, conceptually, it doesn't have to actually be this way, sort of keep the values I wrote off to the side. I haven't actually written them to memory yet. If I commit successfully, I'll write them to memory and everything is done atomically. It can arrange to do that. But if I'm the ugly one that gets shot in the head because I conflict, and I just throw away the stuff I started doing and I start over. And this way you have a very nice model of just atomic brace, blah, brace. Alas, as with most simple ideas, when you start to implement them, you discover the difficulties. Now, I'm going to describe some of them. These are not killers, but do watch transactional memory because this is a very, very important technology to watch over the next few years that we will use in production sooner rather than later. The elephant in the room is, well, what if I do stuff that doesn't touch memory? You know, it's good as long as I'm saying x equals 1, y equals 2, but what if I do console write line? You know, if in my atomic block I say console write line, enter your name, console read line, the user can tell whether I execute that twice, right? There's certain things that just are not undoable and just restartable. The Achilles heel is that some resources are not transactable, so that the usual answer to I.O. is to say, oh, well, there's a lot of transactable I.O. out there now. Windows has a transactable file system. So if you go through a transaction manager, you can actually get a transactional begin, end, begin, commit, retry interface to the file system for many kinds of things, which is wonderful. So why not just have your transactional memory system work together with your transactional I.O. system? Like in .NET, its system transactions is one, and there are others as well. And then life is wonderful. Yes, now you've allowed some I.O., the kind that's transactable, to happen inside an atomic block. But some things like console write line just aren't transactable. They involve a human, for example, or they involve some remote piece of equipment or software. So the idea here is that transactional memory, should it work out, and the question mainly is how much stuff can we allow you to write inside an atomic block, and how fast can we make it work? So if that pans out, we can probably get rid of the vast majority of locks, because most things are transactable or touch-only memory. However, some things will still remain. So after that, number 2 is, okay, our problem is mutable shared state. I've got an object in memory that 2 threads can see, it's shared, and one of them can mutate it, right? I don't care if it's immutable, because I don't care how many threads bang on something and read something. If the location doesn't change, I don't need any control there. And if I don't make it shared, I'm good too. So first, I'd like to have abstractions that reduce the amount of shared state. So messages will help there. We're going to talk about futures. The next thing after that is to use techniques to get rid of mutable state. It's still shared, but it's immutable. So if you look at strings in .NET and Java, you may have noticed that when you get a system string and you append to it, did you ever notice that if you take the address of that or inspect where it is in memory, you didn't actually append to that string, you got a new string, and now you're pointing at it? That's because strings are immutable, which means you don't need to lock them to use them. They never change. And with a garbage collector to clean them up at the end of the day, life is wonderful. So if you have immutable objects or internally versioned objects, if you come to talks like one, I think a year or 2 ago by Andre at this same group, only it was up in Bothell, he talked about how to write this yourself. Then life is wonderful. But what if you can't put it in a transaction, you can't make it not shared, you can't make it not mutable? Some locks will still remain, but hopefully we've sort of kept them in the corner and put the dunce hat on them so we don't have to look at them most of the time. When we do, we still should let the programmer to declare what shared objects are protected by what locks, and then second, what the lock levels are, the lock hierarchies in the system. And some of these things you can roll your own. Like the main thing in the lock hierarchy, and often it corresponds to your actual architecture, your module hierarchy too, very often it can. The idea is to say, okay, locks, every lock is at a certain level, and there are only 2 rules. If I hold the lock at one level, I can only take new locks while I'm holding it at levels lower. So if I take this one, then this one, I can't go here. I have to do it in this order. And therefore, the second rule falls out from that. If I need more than one lock at the same level, I have to take them at the same time. And the way that this gets away from deadlock is because now everybody takes locks in the same order, and you can't have deadlock then, right? Because in the levels, you have to take them in level order. And because you take all the ones at the same level at the same time, the system can just do it for you, take them in address order, say. It can find an order that everybody will respect. But that's what we do today. We need to be able to declare our intent better so that the compiler, the tools can help us figure out when we got it wrong. And just a footnote on that, by the way. Don't think that that solves locks. And, well, wait a minute. Locks work after all. This makes them composable. No, it just makes the use of locks less error-prone. But the problem with those solutions, like lock hierarchies, is that they themselves are still not composable. Because my piece of software and your piece of software has to agree to play by the same lock hierarchy, and we never talk to each other. So those are still not composable. But get rid of locks, get rid of shared, get rid of mutable, and the ones that remain, declare your intent, is, I think, the best strategy to whittle away and get past the problems of locks. Some things that a lot of people have already tried And some of them are good, but these are not bad. They're still bullets. They're just lead bullets, and they're mostly lined up already. Automatic parallelization, we still see some of this. KAI had a nice product that would automatically parallelize parts of your code. Somebody already talked about vectorization. You certainly want to have some incremental benefit there, but those are not going to give you order of magnitude improvements scalably across a number of processors. They will give you a fixed improvement, especially on your data size, but you really want to go further, and there are some drawbacks with what automatic parallelization can do for you. Then people say, well, why don't you just rewrite everything in Haskell? Or get a clue, or yeah, okay, some people like Haskell. So, or functional languages in general. And functional languages are great. They're just naturally parallel, it looks like, because everything is, you know, a rule expansion or something similar to that, right? So it's just naturally parallel. And in fact, the pure functional languages don't even have the concept of a modifiable object. Every time that you modify an object, you get a new copy with a modified value, just like strings, right, in .NET or in Java. Wonderful. Okay, two problems. The reason functional languages haven't taken over the world for this, besides the fact that nobody is really sure whether you can teach them to mainstream programmers and have them actually be usable, it's just people seem to think in a step-by-step way rather than in a functional way most of the time. Leaving that aside, there is this natural parallelism. I expand a rule and I can just expand bits of it in parallel, expand the rules in parallel. The problem is that parallelism is way too fine-grained. It's at the function call level. And it turns out the overhead for parallelizing usually dwarfs that of function call overhead, so that's actually not the granularity of parallelism you mostly want to work with. And this is what I love. The real big advantage of functional languages, the pure ones, is you can have this immutable data. You modify it, you actually get a new one with a new value. And there are two kinds of functional languages in the world. Those that are pure, with immutable data, and the ones that everybody actually uses. Because it turns out that functional languages, out of necessity, have added in-place mutation of data. And once you've done that, welcome to the real world. You're right back to Lockville, because that's the only way you can deal with that. And in particular, I mean, think about it. Like, how many of you really, if you had your choice, would take a million-element vector, change the fifth element, and expect to incur the overhead of copying a million-element vector and getting a new one with that one new value? How many of you would love that as, no, I didn't think so.
That's a straw man.
That is a straw man, but it's exactly the kind of reason why functional languages, the ones that actually get used, have had mutable data built into them, because people can't afford it for large data structures. Then there's OpenMP, which is industrial strength duct tape, but still useful where it's applicable. So there's no question OpenMP is industrial strength. There's also no question it's duct tape. It's not in the language, and we're going to talk a little bit about it in one slide later on. So let's talk about some consequences. So here is what's happening.
Previous slide for a second, sorry.
Previous slide?
Yeah,
Yes.
Where would you put Erlang in this, on this, like, this category?
I don't know Erlang very well. Is it a functional language?
No shared
It's
state.
somewhat functional, but it's highly parallel.
Yeah, so how does it deal with shared state?
It doesn't, they designed it out.
Message passing.
Okay, so it uses message passing. But if I have a data structure, say a vector with a million elements, and I want to change an entry in it, what happens?
You'd have to ask an Erlang expert, which I am.
Okay,
Erlang is designed around getting rid of shared state.
which is a noble effort.
And that's, how do you share a data structure? Well, you can't, so you don't. It's not really a, if your program works at all, it will work across a network.
One thing that I forgot to mention about functional languages, so I'm glad we went to this slide, is even though they have those problems, it's not like, okay, ever rewrite a functional language in the whole world and come back 10 years later and everything will be wonderful. There are some key parts of functional languages that are transferable to our usual imperative languages, specifically lambda functions, the ability to talk about a piece of code as a first-class construct. C# has already added them. And Java and others, the C++ committee now is looking at, has proposals, 2 proposals in front of it for adding lambda function support, which is basically like writing a function on the fly and passing the function around. And if you know functors, it's basically like just automated syntax or writing a functor on the fly. So you don't have to write your own class somewhere else and then write the functor there. You just write a functor on the fly in place and pass it around. Comes from functional languages, give credit where it's due. Turns out that this idea of being able to talk about a piece of code and then pass it around and then let somebody else execute it is a wonderful, wonderful paradigm that we're going to make use of later. So let me talk about some consequences on how we develop software.
Comes from algal, it's much older than the function.
Oh, okay, well, I want to say something nice about the functional. And well, frankly, algal, what's algal 60? You know, everything comes from the 50s and 60s. So read the DDJ editorial I just put on my website. And, like, everything comes from the 50s and 60s. But, by the way, the one-line summary of that guest editorial I wrote for DDJ last month, actually, I guess this month, in the September issue, is that, yes, mostly, like, all the cool things that we've popularized in the last 20 years, GC, generics, templates, all objects, all that stuff, comes from the 50s and 60s. So you may think it's all been done, except that now, for the very first time in the history of computing, mainstream hardware is no longer a von Neumann machine. This has never happened before, and that's why that makes it a really fundamental shift in the way we program, which are the consequences that we're going to talk about next. So I find it useful to put a label on 3 particular kinds of concurrency, and I'll call them order 1, order K, or order N. So how much concurrency do you really have in your application? How many things is it doing at the same time? So order 1, obviously, is it's doing one thing at a time. So this is every sequential application you ever wrote. And it's also, for all those lucky people who've done this, it's every multi-threaded application you've ever written that convoys on a global lock, or is otherwise just doing one thing at a time. So that order 1 doesn't mean single-threaded, it just includes single-threaded. Free lunch is over for order 1, and this is also the class of application that today tends to be very non-responsive. You click on something in the GUI, and it takes 30 seconds to do it. In the meantime, your GUI says, and sometimes it goes white, it just goes away for a while, and then finally it's done and the GUI starts painting again. Responsiveness is also a concurrency issue. One of 2, the performance, the throughput, and responsiveness are the 2 big ones we're going to talk about. Then you have your explicitly threaded apps. So this is a wonderful place to be if you know your target hardware and it's never going to change. Like Xbox 360, for example, you know you're going to have 3 cores, 2 hardware threads each, and you can just write to that. People do this in non-hardware specific environments too, though, non-fixed hardware environments. Imagine that when you look at this number of threads that are active in the application, let's simplify it and let's just make them all be about equally busy, just as a simple example. You've got a first-person game. Notice I didn't say shooter. That would be politically incorrect. But a first-person game, nevertheless. And what have you got to have? Well, you've got a physics computation going on, so let's have a physics thread. You've got a rendering thread to update the screen. And maybe another thread you're going to use for all the AI, the monsters, which actually takes up a surprising amount of time if you want monsters. I mean, fellow players or non-player characters. Do anything reasonable. And then maybe you piggyback on that guy, the player input, which actually is lightweight. And let's just simplify the assumption and say that they're about the same performance. And they wait on each other, but they do about the same amount of work. Great, so I run that game on my legacy, so 1980s, single-core machine. And it runs, right? Frame rate might not be great, but it runs. I go up and I go to Best Buy and I buy a dual-core machine, which I can now do. I run that very same binary on a dual-core machine, and it will be faster. Won't be twice as fast. The reason it won't be twice as fast is because I've got to somehow map 3 equal pieces of busyness of work down to 2 cores. And well, how am I going to do that? Well, I can run maybe physics on core 0 and rendering on core 1, and now I can have 2 major choices, among others. I can get more complicated. But where do I run AI? Well, maybe I can run it on core 0, which means that core 1 idles half the time because it's waiting for physics or something, and waiting for the other core. But I've still got a 50% improvement. Or you might say, well, wait a minute, that's what modern operating systems are for. I'll just run all 3 threads, and it can go pick 0 and 1, and it can take the 3rd thread and just run it sort of half on each. Of course, be aware of the cache sloshing you're going to get. You are not going to get perfect performance out of doing it that way, depending on how much data is being used. And some designs are actually trying to make that cost go down so you do get 2x performance on those chips. Then this Christmas, I go out, because Intel told me, it's promised me that I can, and I go out and I buy a 4-core machine. And if they didn't ship it on time, I'll go and buy a 2-socket dual-core machine, which will still have 4 cores. Right? And I run the game on it, And it will be faster, but it will be 4 times as fast as the original because there's only order 3 parallelism in there. It's a fixed amount of parallelism. And then I buy my 8-core machine and nothing happens. And my 16-core machine, and $10,000 later, more nothing happens. And then you start wondering about, okay, well, who's going to buy these machines? Well, not for these ones. What we actually would like is order n concurrency. Instead of a fixed amount of concurrency hardwired into the application, imagine an application that's just a sea of work items. Fat ones, slim ones, long-running ones, short-running ones, CPU-bound ones, I/O-bound ones, just chunking your application into divisible units of work that don't depend on each other. Maybe one's waiting for another, but you can express them as these chunks of work. And then on my 1-core machine, I spin up 1 worker thread, and he just spends his entire life just taking an item off the queue, executing it, taking an item off the queue, executing it. And when I upgrade that to a 4-core machine, that very same binary wakes up when you launch it and says, oh, look, I have 4 cores. I'm going to run 4 threads, hard affinitize them to the 4 CPUs, if Windows lets me, and I will then just have 4 guys that are consuming the queue. 16 core, 16 worker threads. And you can see how this model, at least in concept, and then you've got other issues like memory, scales to at least where you're no longer CPU bound, but you're bound on I/O, memory counts as I/O, or other things. And this is a wonderful, wonderful model, except that pretty much nobody builds applications this way today. It's a great model, but we don't know how to do it. Well, actually, that's not entirely true. We have some ideas. Virtually all applications are order 1. Virtually all the rest are order K. And almost nobody does this. Now, OpenMP is kind of in this category because you spin it up, it creates a right-sized pool of worker threads. And so for the stuff that you do through OpenMP, those loops you can parallelize, it will actually right-size the hardware. This is a step in the right direction. Look at background workers in Java and .NET. Also a step in the right direction, but currently too cumbersome to use. So what we'd like to have, just as we used to do work in assembler, we'd like another level of abstraction. So I want to ask about the guys, if there are any of you in the room, I see a few gray hairs, who might have been doing like the actual machine language. Most of us think assembler is machine language, but you ain't done machine language, and I ain't done machine language, until you've poked particular values into particular memory locations to make the machine do stuff. And I'm not even going back further and talking about wires in the back. But let's just start with assembler. Okay, Pete, yeah. Well, I said poke on purpose. Yeah. So you start with assembler, but most people quickly went to higher level languages, C, Fortran, COBOL. And so at this higher language, you have abstractions like functions, procedures that you can reason about rather than just a series of machine instructions in an assembler environment. And then on top of that, then we went through another generational advance and we built objects. Classes, virtual functions, inheritance, all these abstractions that help us build composable software. And you can build OO class libraries, and you can build OO programs in C. Windows SDK did it back in the Windows 3.1 days. Everybody did. It's all those APIs where you take a handle as your first parameter. So you have create window returns you a handle. And then you pass resize window, handle, comma, parameters. Right? It's OO. It's just you're having an explicit this parameter. I mean, the C API does it, right? fopen is a constructor, fclose is a destructor, ftell, which takes a file as its first parameter, is a member function. It's just you have to do it by hand, and there are lots of ways to go wrong because you're rolling your own vtables and because you don't have any language support for the idioms that you're working at. We need the same thing for concurrency because programming with naked semaphores is really feels and is a lot like programming in assembler. Today, the status quo is threads and locks. We're all writing code in C, essentially, from a concurrency point of view. And we need the objects and virtual functions and those kinds of abstractions. And the reason that space is empty, by the way, isn't because we don't know what goes there and we have no candidates. We have a good 20, 30 years of candidates of abstractions to go there. There are hundreds of them. The challenge is picking a small number that covers the space that hangs together well that people can understand. And it's toolable. And so that's an important need, is to fill that space that way. So remember the story of the blind man and the elephant? The blind man and the elephant? The guy at the end thinks the elephant is a rope. The guy at the side thinks the elephant is a wall, right? And they're all partly right. And concurrency is a lot like this. I borrowed this slide of the next couple from David Callahan, who now works actually on this floor here, ex of Cray a year ago. And his vision is very interesting because everybody knows, I mean, those of you who've done multi-threaded programming, well, you know what multi-threaded programming is all about. You know what the concurrency problem is, right? For your application and for your application. And so we each know what it means for us, for the kinds of problems that we've had to solve. And you get 3 people in a room and you'll quickly, after 20 minutes, get 5 different opinions about what the concurrency problem is as people have their different perspectives. This is not, by any means, an exhaustive list of the words that come up in concurrency. Just a very small sample because the screen was only so big. You talk about protocol, fine-grained, hierarchical, timeout, cancel, dismiss, acquire, schedule, associative throughput, and parallelism, until people just decide you must know what you're talking about because you're using all these words. And they really fall into 4 major categories. Remember I said how there are 2 pillars of concurrent application? There are requirements for responsiveness, so you can start doing something, but still have the application responsive while it's doing it in the background. That's pillar 1. But the other one of, I push a button and I want the result faster. I want to actually use 8 cores or 16 cores to get the result faster. So that's column 2. You're doing things like fork join to parcel out work to 8 cores and then merge the results again. And look at just these 2 columns for a second, because they are very different requirements. And a lot of the time, when people get into a room and they start throwing out terms like concurrency is a rope or concurrency is a wall, it's because they're using words with the wrong meaning or from the wrong column. Because some words come in more than one column, but not usually with the same meaning. For example, asynchronous agents is all about how do I kick off a task and have it run asynchronously while I'm doing other stuff. So I care about things like, it's all about responsiveness so I can keep doing other stuff. I care about dialogues and protocols. I definitely care about messages. That's a key abstraction in this. I care about timeouts, because what if it doesn't come back? And then you talk to somebody about your message passing system. I mean, people do this call of an open MPI today, right? We just want abstractions around it. So you're talking about your message passing system, and then some guy in the room says, well, what's the overhead? Wrong column. You're talking about something different now. Or how do you make this data driven? Is it systolic? Wrong column. That's not what this is about. It's about having an asynchronous piece of work, and we message to and from it asynchronously to get results in and out or to communicate. Concurrent collections is all about being able to do work widely for throughput. So there I care about being able to take an array and work on 1/8 of it in parallel if I have an 8-core machine, for example. I do care about overhead because I care about the overhead of spinning off this worker thread pool, of bringing the results together again, because I'm all driven by time to result. That's the key thing in column 2. Column 3 is different from these columns because these are conceptual ways, the kinds of parallelism we want to express. We have different reasons for wanting responsiveness or wanting throughput, and both of them can exist in the same application. But both of these use column 3, which is basically, great, how do I manage shared state? And today the answer is locks, and we'd like to fill in more things here. But notice things like atomic and consistent and invariant. So these are some of the words that come from the database world, from ACID. Having something be atomic, consistent, isolated, durable. So it's all about transactions, right? And so locks and transactions, how to manage shared states here. And then some of the words that sometimes fill in are from a different really world entirely, not specific to concurrency, just dealing with real resources, things you read and write and open and close. So we'll come back to this, but it's useful to look at the concurrency world in these 4 columns to be able to reason about what we're trying to do. So we want to...
Are you making these slides available somewhere?
Yes. Versions of these slides are already available on my website from previous talks. This contains extra slides that haven't been in some of the public ones before. But I'll make it available on my website and through David.
Get this one?
Yeah, you can get this one. I'll make it available to David. So David, where are you? You'll ping me if I know, right?
That's right.
And he knows where I live, or at least Google will tell him. And then it'll happen, okay. So we want to enable applications with lots of latent concurrency at every level, right? So that it runs well on today's hardware, runs better on 4-core, runs better on 32-core, as much as we can. We want to have abstractions that let us fill in those columns around messaging and asynchronous agents, around concurrent collections, and around getting rid of locks and having transactions. And I'm not going to talk much about tools, but boy, we need a lot of tool support too. We just don't have, not we Microsoft, we the industry, just don't have really good thread debugging tools, concurrency debugging tools, profilers. There are some out there. They tend to be either not very mature, or the mature ones tend not to scale. So they work well on very small projects, but you want to do something big like Instrument Windows or even Visual Studio, and good luck. It's just not, they're just not there yet. You want better debuggers, like to go back in time to figure out how something happened, to be able to follow messages through, which are kind of like function calls, but they're asynchronous, and be able to step into and through those. And so there's lots of stuff that we want to do in tools. This is requiring work at all the levels, from the hardware to the OS, to the runtimes, to the languages, to the tools, to the applications. I'm mostly talking about the languages part, but all parts of the stack above and below have to fit well with what we do. At this point, it does remind me, how many of you remember an incident in the news, about 6 weeks ago, with a guy named Mel arrested for DUI in California? Remember that? Yeah, well, most people don't know Mel was actually a software developer. And it's really interesting to notice just how awful a reaction this hardware push for concurrency has had on software. It's really driving people to distraction. In fact, I was looking at the police report again the other day. It mentioned that Mel was the lead architect of the Passion of the Code. And in the quote from the police report, it says that he was distraught and screaming. And he says, "The hardware guys are doing it to us again," he reportedly said. "It's the hardware guys. They're responsible for all the software problems in the world." And say, are you a hardware guy? It's okay, there was a statement of retraction released the next day where through publicist Mel said, "I acted like a person completely out of control and said things that I did not believe to be true and which were despicable. Hey, some of my best friends are hardware guys, really." We don't want to become philosophers, and the impact on software could drive us to distraction, but let's talk about things that are being done to actually enable programs that will work well on the current kind of hardware. So some of the stuff that's already been available, if you look at OpenMP, which Visual Studio now supports, Visual C++ now supports, as well as Intel's and other compilers. Memory model work going on, including work that I'm doing for memory model across Microsoft platforms. Java and .NET and Visual C++ have already done some work in that area. And C++ OS is currently working on standardizing a memory model, which, frankly, a memory model can be described as something that nobody should know about, but everybody relies on, and we don't have one, so we need one. For details, see the references at the end. I'm going to talk a bit about the Concur project, but there are many other kinds of projects. Transactional memory is a really big one I've mentioned already. People are experimenting with extensions to languages, their own languages like Fortress and C Omega. So people are doing a lot of fruitful work, and I'm going to argue that a really important piece is extensions to today's languages to let us write concurrent code. New languages are good too. I'm not saying people should drop what they're doing and stop working on them. But we're not going to bring the mainstream of software into a parallel age quickly if we wait for everybody to rewrite their code in a new language. What we need to have is incrementally adoptable extensions to existing languages to really make things take off and bring it to the mainstream, just like we did with objects, just like we did with templates. And so the Concur project goals in one slide are really 6 steps, the last of which is to re-enable the free lunch. So first you need higher level abstractions. And so higher level abstractions specifically above threads and logs. Now, I'm going out on a limb here, and some of you may want to shoot me. If so, I hope that you check your guns at the door. But to me, any programming model that ships 2 or 3 years from now or 5 years from now, where thread with a capital or little t is still a central abstraction, is worth looking at. It's already a failure on its face. It's not at a high enough level of abstraction. That doesn't mean most won't be. C++ is now belatedly standardizing a thread type, or is working on it. But that's so 80s. We're into the 21st century now. I have to say that every so often because my wife really hates the 80s. I kind of like them, but I lose. For today's imperative languages, in particular, people aren't going to go rewrite the world at Haskell, even if they should. I'm not arguing if they should, but they won't. Not enough of them. And in particular, what extensions can we add to existing imperative languages? And I happen to be looking at C++, but the same kinds of things can be added to any imperative language, C# or Java or anything like that. That supports the same range of concurrency granularity, supports asynchronous agents and concurrent collections and interacting infrastructure well, so that people like you and me can write correct and efficient concurrent apps that I can actually reason about what it does with some confidence that I know what's going on. I mean, today, when you write concurrent code, how many of you have gone to the trouble of multi-threading your application, run it the very first time, it's okay if it fails the first time, and discovered it was not significantly faster than the single-threaded version? How many have gone through that? Why? What are some reasons why that happened to you?
The algorithm was wrong.
Algorithm was wrong, okay? Anything else? You need to redesign, yeah.
Yeah, you have to rethink
That word often comes up.
You couldn't find the parallelism in the code.
Yeah, Amdahl's law bit you, so you just couldn't find the parallelism or invent it. Anything else?
It's dominated by the serial part of it, where it's synchronizing.
Dominated by the serial part, okay, Amdahl's law again. And if you want to say the serial part as in serial ports, then it could be dominated by that too, right? By I/O. I mentioned another one I think somebody said.
It's not CPU wasn't the goal to run it faster.
It wasn't your goal to write it faster. Okay, I didn't mean to do that. Or you write wonderful lock-based code and you're convoyed on a global lock. If you look deep into Windows right now, there are lots of graphical structures that are all protected by one single lock. And so, even in Vista, and you will see this in Mac OS X, you'll see it in other kinds of systems as well, but you will see certain things that should be snappy, but take half a second or take a quarter of a second, which is longer than we want, but it works, but you can see a little bit of lag because it's contending on a global lock, or a pretty global lock for a particular set of data. And so one way you can deal with that is make things more fine-grained, but then you have more things to juggle and more opportunities for deadlock. So to write correct and efficient apps that I can reason about and that is toolable is very important. And I mean, this next part, I love this next part. With lots of latent parallelism and not lots of latent bugs, we can do the second one just fine today. We know how to write software with lots of latent bugs, especially concurrency bugs. And that we can map down to the user's hardware, so it gets better. It ages gracefully. It gets better on your hardware again. So I'm going to talk about some features, but there's a lot that I'm not going to cover. But just FYI, what you're going to see in the next few slides isn't the whole thing, but it flows from those requirements and the kinds of ways we need to write software differently. I'm going to talk about the two major chunks, which correspond to the first two columns in the picture I showed earlier. When you talk about asynchronous agents, the idea of having active objects that conceptually run on their own thread, or active blocks, which are conceptually a little lambda function that you just say, go run this asynchronously, are ways to just spin up lots and lots of asynchronous agents. At some point, we're going to have to join with them, and we can do that using futures, and I'll show that. And so all of that is going to be about the first column, which is the asynchronous agents. But sometimes it's not good enough to fire something off and still be responsive. Sometimes you actually want the answer faster. And that's when I want to be able to use algorithms over data structures more efficiently. And I'm going to talk about how we can, one way that is a sketch, it's still under development, but it looks promising, about parallelizing standard STL algorithms and actually having it be parameterized by the kind of traversal I want to do. So let's first talk about active objects and messages. The nutshell summary is that conceptually, and I underline conceptually because I reserve the right to do it differently to you. I said it that way on purpose. Is conceptually every object runs on its own thread. It might be more efficient to do it some other way, but you can think of it that way. When I do a method call from some other code to an active object, like in the code below, I have an active C object and I call F. It just looks like a normal number function call, right? That is actually an asynchronous message that does not block here, doesn't go into F, execute it, and then come back and continue executing. It fires off a message of type F to object C with the given parameters, in this case none, and immediately continues executing without waiting for this to actually happen. We'll talk about return values in a minute. Sometimes you actually want return values. One of the nice things about this is as this C object here is going through and living its life, think of it as inhabiting its own thread, where the very first thing it does is it runs its constructor. And the way it does that is because it's just a little worker that's just running and looking for message calls coming in on its queue. The first one happens to be the constructor, so it runs the constructor, sets itself, and then it spins there efficiently, waiting until messages come in, function calls, and maybe if it gets a bit behind, there could be a queue of them, but it just surfaces them as fast as it can. When it sees the F come in, it takes the F off its queue and executes it, and then it takes the next thing off its queue and executes it. All on the same thread, conceptually. So one of the nice things about that is if you put in a few controls, like you don't allow programmers of this class C to hand out pointers and references to internal variables, so to create shared state that way. If you turn off those knobs, then you actually have an active object whose private members are never shared. That falls into one of the things we wanted to do to get around locks, is to reduce sharing. So if an active object is the only thread that can touch its own private state, everybody else messages with him. Now, I don't need locks around that active object. Now, yes, when I make a call to an active object and he makes a call to another active object, if they wait for the result, you can still get blocking cycles and get deadlocks that way. But you don't have to use locks to control the shared memory. At least inside that active object, you create a little silo, which is still an improvement. Let's see. It also turns out to be nice to be able to express thread and task lifetimes as object lifetimes, because the language already has wonderful support for objects. I can talk about lifetimes, when things get constructed, when they get automatically destroyed, when I have members that are directly held and their destructors chained to get run automatically. And so it's very nice to be able to leverage all of those rich semantics built into C++ in particular, more so than other languages, for object lifetime management support, and just immediately leverage it for thread and task lifetimes. And there's a slide again on that a bit later with a code example. I might have mentioned sometimes you want a return value. I couldn't get very far pretending you'll never want to see a return value, or an out parameter for that matter. And this is where futures come in. Now, most of what I'm talking about, let me just step out of the presentation for a minute into my ISO C++ hat. Most of what I'm talking about is some silly Microsoft internal research project. That's all it is. It's not like a shipping product or anything. It's work that's being done to see if it pans out. If it does, then it can be worked into something that can be shipped and supported. But in the ISO C++ world, nothing of what I just said about active objects exists in C++ as it is today, or in C++ OX, the next version that's currently well into development, mostly done development. Futures, however, are under active consideration, and most of the code in the next few slides, I have as much as anybody can predict what the committee will do, I have a good confidence that, at least 50-50, that you will be able to compile this code in ISO C++ when we ship the next standard, and then when people actually implement it, which can be some N months after that, or weeks or years, depending. So futures are interesting. They're already in Java. They're spelled with a capital F, but that's just, Java. So if you have a return value or an out parameter, I'm going to call an active object like calc and call it with calc total orders. Give me the total of the orders. Now that's going to return right away, but it may not have executed yet. I'm going to continue, so I still would like to know the result, which is of type double. So the way I hang on to it without blocking and waiting for it to execute is to get a future double. It's like a ticket that is redeemable for a particular, but that word can be misinterpreted. So a ticket that you can then redeem for a double at some point in the future. If you want, or you can litter and leave it away if you decide you didn't want the double after all. And then I do potentially lots of work, and then when I want the answer, I say tote.wait. And the current ISO C++ proposal doesn't have .wait in there, it just has tote paren, like just a function call operator. I still think wait is better because it's explicit that you might block here, but probably in ISO C++, when we standardize this over the next few meetings, so over the next year or so, probably that .wait will be gone, which I think is a shame. But I'll argue for that in a second. So any questions about how the future works? It's an asynchronous value. It's gonna be a double when you finally ask for it. And when you do ask for it, you'll either get it right away if it's ready, or you'll wait until it's ready, and then it'll turn into a value. And so the way to think of weight here is it's a named conversion function from future of t to t. You say weight, and you convert a future of t to a t. You redeem your chip. There, I said it. So I happen to think it's a good idea to have weight be explicit. Several reasons. A lot of people notice here that, you could make this work so that there's an implicit conversion from future of t to t. So all you would have to do is write, not the weight part, do something with tote, and it would just work, right? After all, you know that it's taking a double. I have a future of double. You know that in the language the conversion is necessary, so you can just do it implicitly, right? I wouldn't want that. For me, if I were programming, I'll tell you why. This potentially lots of work. Could be, a million lines, and I'm not exaggerating, because it may be 50 you can see, but then after you do all the function calls and the call stack that's underneath it, it could be a big chunk of code. And the whole point of calling total orders asynchronously was because I don't need the result yet. I'm going to do all this other work that's independent and get nice parallelism, and then finally when I need it, I'm going to ask for the result. Now let's say I didn't have to write weight. So you and I, because we're smart, we know not to touch tote. We're very careful to leave it over there and not even look at it. And then finally we say tote here, and we implicitly wait if you don't have the weight, right? Wonderful. 6 months later, Joe Maintenance Programmer, who is probably your future self, comes in, forgets that he was being very careful not to touch tote, and says, I wonder what the value of tote was, and writes it to a log file or something right after the call line. And suddenly, silently, that compiles, and the application is a lot slower, and there's no visible cue why. It compiled just fine, no compiler warning, no nothing. At the very least, if you tried putting this in, log file tote, if you had the explicit weight, at the very least you'd get a compile time error saying wrong type. You have to call weight if you want to convert a future to a value. There are other reasons too. For example, if you wait for a future, well, what if the thing that's producing that value didn't succeed? What if it threw an exception? Well, you actually, if you were doing a normal function call, you would want the exception to come to you. And in fact, one of the nice things that we're working on doing in ISO/C++OX is to say, okay, well, for what kinds of exceptions can we actually take the exception off that stack, move it onto your stack when you wait for it, and there could be 3 people waiting for the same result, right? And each one gets the exception coming back out when it waits for them. And so we're going to hear about clonable exceptions and things like that. And if we can't convert it, then maybe just a generic one, exception happened, or something useful like that. Well, if that could happen when you just touch tote, you just say its name, just saying its name could give you an exception, that just seems a little subtle to me, but it might just be me. And there are some other reasons why you want to treat a future of t differently from a t. It could be, however, that in some languages, remember, this is intended for all imperative languages, in some languages which are designed for non-specialist programmers, so people like who are just writing little business apps or writing Visual Basic code or something like that. For them, you might want to make futures completely implicit. You don't say future of t, the double just is a future of double when it needs to be. We infer its type. And when you say tote, then you block. And you still have the same problems. You can silently lose concurrency. The exception can be thrown out of this use. But it might be people who are programming those languages or designing those languages may decide that that's better for their customers. They just want it to be easy for them. And maybe they're not so performance sensitive. So if he does an early looking at the tote and he loses the performance, oh well. So that could be acceptable for a particular kind of program or a language. But both can be built on the same runtime, so that they're both interoperable, so that somebody in Visual Basic can write this and somebody in C++ can write this, and they work together. You can spin up the active object in Visual Basic, have a future with an explicit weight in C++, and vice versa without the weight. So that interoperability is very important and something that we're also working on internally. Let's just compare even this to what you have to do today. So today, if you use the .NET design guidelines, here's what you use for the async pattern. How many of you have used the async pattern and IAsync results in .NET programming? Just curious, how many of you love it? I saw a wince, but is that sort of a wince that's bad, or I don't know if I love it.
It's you
you said in that there's a sync async thing that Schmidt talks about in his ACE.
Oh yeah, there's ACE as well. A lot of frameworks do this.
And that's the one I'm familiar with.
So let's look at the way it works in .NET if somebody wants to do this in .NET. And there's similar facilities in Java, in ACE, and other places. So typically what you do is instead of having a single function call that takes some parameters and has a return, you break it into two function calls, one at begin, which takes all the input parameters, and a callback, optionally, to get called back when it completes, and a cookie that you pass around to remember what you were doing at the time. And you get this thing that's remarkably like a future, but it's called iasync result. It's a lot like a future. It's just a hand-coded pattern, and that makes it a bit harder to use. Then you have the end method name, and it takes that future, that iasync result, and it takes all the output parameters so you can write back out through them, and it gives you your return value back. So basically you call this guy with the input parameters and some other gunk, and then when you get called back, or when you explicitly wait, then you call the end version and actually get your answers. And this is just done by hand. And lots of people have reinvented this. This is the .NET version. Outlook did virtually the same thing in native code internally, and a lot of people have reinvented this.
Moving Corbett.
Corba, okay. I don't know Corba very well, so they've reinvented it too?
Yeah.
Well, if something's worth reinventing once, it's worth reinventing 100 times, and usually it's. So what are some issues with this? Well, it's kind of intrusive. You need to break apart the functions and know which ones are going to be called asynchronously. And that one you can actually mitigate, because I'm going to show you in the code example, I'm going to even make use of some C# features that let you not have to know that, because they use asynchronous delegates, so you can call any old function with a begin end, and I'll show that. So you can actually work around the first point. What you can't work around is that it's complicated for callers, that it's a hand-coded pattern without language support, when really what we need is not to be programming at the C, threads, and blocks level. We need an abstraction. This is not quite it. And it's brittle. So for example, one of the things you must remember to do, if you call begin and launch a function, even if it later turns out you don't care about the result after all, you must still call end, which waits for it, and which, among other things, is the opportunity for that asynchronous piece of work to clean up any data structures it might have allocated. And it's true that many times end won't do anything, and it won't have allocated data structures, but enough of them do and you won't know. And this is brittle enough that even certain very well-known people whose names I won't mention, but whose initials are Don Box, who know this stuff, who are certifiable experts, for some, whatever, that publish things like, well, you don't have to actually call the end one if you don't care about the result. And then if you look in a blog about 3 years ago or 2 years ago, Don corrected that, saying, you know that part where I said you don't have to call the end version if you don't want the result? I sort of lied. You actually do, or you're going to leak resources. Sorry about that. Have a nice day. So let's see what this turns into. I'm going to give you a programming problem. I waited till later in the evening when you're good and tired to give you a programming problem. I want to implement the above, which I'm going to show in some pseudocode. I want a function called process, or if you're from Canada like I am, process, that uses some other services and takes a timeout. And what it does is I want to get the result of calling work1 plus the result of either work 2 or work 3, whichever finishes first. They're redundant requests to different servers, or they're different algorithms for computing the same result, or in some ways they're redundant. And if they complete within the given milliseconds, I return the result of work 1 plus either 2 or 3. Otherwise, I report that I blew my time budget. Typical async code. I mean, these are pretty simple and common kinds of requirements that are illustrated here. 2 or 3 common kinds of requirements. So how do I write that? Here is the best way I know of to write this code in C# using .NET and using C#'s nice features for making asynchronous calls happen. So first I declare some delegate types, which are just basically pointer to function types, same kind of thing. I'm going to need one for a delegate for work 1, which is going to take an int and return an int. I'm going to need one that takes a string and returns an int, which is work 2 and work 3. I need a third one called cleanup delegate. You might wonder where that is in the requirements, but all will become clear. So in process, I take my parameters. First, I'm going to assume I'm going to fail. I'm going to blow my budget. If I get the result, I'll replace it. I need to have a flag of rules that reminds me whether I've called end invoke yet for each of the three things I'm going to fire off, because I have to call it exactly once for each asynchronous piece of work. And I'm going to calculate right up front when I have to end by, when my timeout is going to be. Because I can't just pass in a number of milliseconds, because I can't do a single wait. I'm going to have to do multiple waits, which means I couldn't eat up time each time, and I have to know in advance, okay, I've got to end by here, and then compute how much is left each time. So first I'm just going to spin up a new delegate where I'm going to call work 1. Here I invoke it, begin invoke, with the parameters 42. Parameter 42, and then null cookies, because I'm not going to use the callback features. Just a small thing here. I personally find it icky, but not horrible. But notice I can't write a normal function call, like work1 paren 42 paren. I have to break it up, take the pointer to function to work1, then separately pass in the values. You know, not the end of the world, but I'll just note it as a deficiency. Next, I need to fire off work 2 and work 3. So I do something similar. I create a delegate for each one, pass x, y, z, z, y to each one, and I'm going to remember their async wait handles, because I'm going to have to wait on these guys. So I have a little array of wait handles. Now I'm going to say, okay, great. I don't know how long that took, but whatever time I've got left, I'm going to figure out how much time I've got left in my budget, and I'm going to wait for any of those two, work 2 or work 3. The reason I have to do this is because the only two choices I have is wait all or wait any. I can't say wait for 1 and 2 or 3, so now I'm doing the 2 or 3 part. If that didn't time out, then I know either 2 or 3 is done. I figure out which one it is. Is 2 completed? Yes. Then I'm going to call end invoke, notice, on 2. And I'm going to remember that I called end invoke on 2 by setting flags of 1. You notice that's off by one thing, zero-based array. Otherwise, I'm going to end invoke 3, which gets me back the result from 3, and remember that I called it. Great. So now all I got to do is wait for work 1. Back to finding out how much time I've got left. And then I'm going to wait handle, just wait 1 on him. And I'm going to, if that completes without overflowing my time budget, I'm going to call end invoke on that. Remember that I called end invoke, and now I've got my result. It's 1 plus the result of 2 or 3, whichever one that was. Easy, right? Oh, I'm not done. Because we haven't cleaned up all the end invokes yet, right? In fact, we've kept track of which ones, but we might have done 0 or 1 or 2 of them. So the next thing I have to do is fire up another function, which I'm going to write on the fly using essentially a lambda function, an anonymous delegate in C#. Basically, this is just writing a function in line and firing it off asynchronously, which is kind of nice. And I'm going to say, oh, if I didn't end invoke the first one, do it, and so forth. I'm going to then begin invoke that delegate, immediately pass another anonymous function to it as to what to do when it's done, and then end invoke itself. So, you know, pull in the edges of the hole after it. And then, so I fired that off, that asynchronous piece of work, and now I return my result, and this asynchronous piece of work is still running while I've given back the result to clean up anything I haven't cleaned up yet. Oh, I saw somebody say, ouch. Okay, this is what you write today. Here's the code in Concur with futures and active blocks. And you could do something similar if the services were already active, you wouldn't need the active blocks, and you could write it even more briefly. But basically all you do is you say, these are all futures of type int. I'm going to start work 1, work 2, and work 3 with normal function call syntax. If those weren't already active objects, I could just wrap them in active brace blocks, run this piece of code asynchronously. And then I'm going to say, okay, I have this future group, which is this future, future 1, and either 2 or 3. So any Boolean expression, any Boolean tree of futures can be combined into a group. I'm going to wait for that group or my timeout. And then, if the group is complete, I'm just going to return 1 plus either 1, 2, or 3, whichever. So 2 or 3, you can have a future group of that type, which is of type future group of int, or actually, yes, of int this time. and then takes the result, and that's the whole code. I personally find that much easier to reason about. And I think it's kind of icky that Java makes this easier than C++. Because you can almost write this in Java. It's about twice as many lines of code. But compared to the alternative being 10 times as many lines of code, that's still a big improvement. So active blocks I've already introduced. The nice thing about this first example on this screen is here I'm just saying, okay, do this piece of work independently, do this piece of work asynchronously, and so forth. Active foo of 10, active A arrow B of C, active new T. Hey, you don't want to go wild. We're going to see in performance measurements just how low we can go for the overhead to make it worthwhile spinning off something into an active block. But we know we can go down to at least about 10,000 cycles or so of worth of work, 10,000 instructions or so, which is still medium sized, but we'll see how far down it can go. But the nice thing about this code in the top is it exactly implements my primary goal for this, which is to make it easy to take existing code bases without just rewriting them and incrementally add concurrency so that just a small change, you can immediately start to see some benefit. You don't have to rewrite in a whole new language. You don't have to stay with your language, but re-architect your code to fit into somebody else's framework before you see any benefit. You can start changing just a few lines and immediately start seeing some benefit. And in particular, the yellow stuff is the stuff that wasn't there before. The white code is the code that was already there. That might have been written 10 years ago. That's the goal anyway. And then we wait for the futures because the types of those things now become future of whatever instead of whatever. So we've seen some idioms. Here's just a little menu of idioms that you can put these very simple things, just these active blocks and futures together in interesting ways. So we already saw this one. I'm going to call a plain object or a plain function. I just put active around it, and now I'm calling a synchronous thing asynchronously as a unit of work. What if you want to do the opposite? What if there's this asynchronous function, like this active object function, but I don't care it's asynchronous, I need the result right away. It doesn't buy me anything in this point, that's fine. I just call the active objects method and immediately wait. So that sort of flows out of the fingertips. Or I could use the non-member version, which is the wait this. But again, I can see what I'm doing in the source code pretty easily. Here's one that's a little subtle, and if this explanation doesn't do it for you, think about it a little more later. But the idea is, okay, if I've got this synchronous operation, instead of calling it synchronously, I will call it asynchronously and immediately wait. What on earth could that possibly buy me? Two things. First, I've got out from under whatever locks I've been holding, which can be important, especially to avoid deadlock situations where I don't really need the locks that I might be holding at this time. The second thing that it buys me is that I'm interruptible, because one of the things that we're currently playing around with in the design is for you to be able to request that a thread cancel. And if you've ever done thread programming, and as soon as I said the word cancel, you probably cringed inside and said, Herb doesn't know what he's talking about. If he's talking about thread cancel, everybody knows that's stupid. It's stupid if you shoot a thread in the head, right? Everybody learned that, right? Thread cancel, the thread abort is just terrible. Raising an asynchronous exception in somebody else's code, they get no chance to clean up, they can break it any time, it's just awful, right? It is a small change, but a very, very, very important one for somebody to be able to request to cancel your thread, and the next time you call wait, it throws an exception saying somebody tried to cancel you that you can catch and do orderly unwinding. And you're not going to get it randomly in any addition you might happen to be in the middle of, but specifically at wait points. So that's what this lets you do as well. So I'm going to do this long operation, but I'm going to stay cancelable because I'm not going to wait for it immediately. But if somebody tries to cancel me, I can immediately respond to the cancel, abandon that operation. In this model, it'll still keep running, but I will be able to clean up what I'm doing and be able to respond immediately to that cancel request. So this is an important one. And here's a cool one, which is sort of like the end of the C# code we just saw. So let's say you've got a future, and you know what you want to do when the future materializes, but you don't want to block and do it now. You don't want to wait for it now. You want to return and do some other stuff, but you know now what it is that needs to be done. Spin up an active block that waits for the future and does whatever you're supposed to do with it. So basically, split off a piece of code who's going to do the right thing when it materializes, waits for the future, and then finishes up, cleans up. So just a couple of very basic tools, active blocks and a future and wait, can be combined pretty powerfully. And this is the kind of thing where I said, none of this is new. You can find active objects in actor languages 10, 15 years ago, if not 20. You can find futures going back, at least the same amount of time. So I don't claim to invent any of these things. Nobody should. Everything old is new again. The question is, out of the sea of hundreds of abstractions you could pick from, what is a small number that hang together well that cover the problem space? And that's sort of an example of what we're trying to do here. So I talked a little bit about this already. Because we can talk about objects, about threads and tasks with object lifetime semantics, when an object goes out of scope, we call it destructor, right? So we can then wait for the thread to end. And we can nest them so that one task owns another task. And when one goes out of scope, we wait for it and all the things it owns to end, because destructors are the only things that do block, because we're waiting for the end. We enqueue the destructor, and then it keeps on running, and it can take the destructor whenever it wants. When it does, until it does, the caller blocks. So we can express thread and task lifetimes and hierarchies of them pretty well.
It's aborting instruction?
What's that?
It's aborting the operation?
No, it's waiting for the request. So every member function call, this is the only place in the whole design where you wait implicitly without seeing the word wait. This is the one exception. And the reason is this. Just to understand what's going on here. Every member function call to an active object is a message, right? Destructor is the same thing. It's just a message. You're firing a destructor message, which goes into the guy's queue. And the only difference there is, one of the things you can choose, it seemed like the right thing to do was implicitly wait then. Because if I've got this object on the stack, this C object on the stack, and I call this destructor, I should implicitly wait for the object to keep pumping whatever messages were before that, and then whatever it chooses to do, then take the destructor message, finish it, and then I can continue. If I didn't want that semantic, it's easy. I just say new C instead of C on the stack, and then I can return and do whatever. See, I can everything I know about object lifetimes, heap versus stack, immediately transfer intuitively correctly to also thread lifetimes. If I want to wait for its destructor, I put it on the stack. If I don't, I put it on the heap.
Yes, but if you have an exception, you expect the destructor to have an abortive semantic, to abort that same operation immediately.
So
Unless
if you have
otherwise-
an exception where?
If you have this scope, and in the middle there is some exception,
Mhm.
you expect like immediate abortive semantics. It's
Well-
more like intuitive for me.
So the question is, if I have a block of code and I have an active object, then let's just say he's on the stack.
Okay.
If I then have another 100 lines, and in there somewhere an exception is thrown, what do I expect to have happen? So option one is to say, I expect to immediately come out of this scope and not wait for the guy to finish. Well, if I'd wanted that, I'm going through the options. That's option one. To do that, I would just say, okay, new C, and then I'm disassociated, I'm not tied to his lifetime. If an exception happens, he keeps running, but I escape out of my stack frame, and I'm not going to see his results, or unless I've passed on futures to somebody else already. Option two is to say, well, if an exception happens, then I want to leave the scope and clean up. One of the things I want to clean up is this task, and option 2A is let him keep running until he's done, wait for that, and that's my cleanup, and then I continue. Now I know he's cleaned himself up, because I've asked him to destroy right away. As soon as he does that gracefully, I'll continue. Option 2B is I want to shoot him in the head, in which case I can actually call cancel on him if I want to. If I can have try catch, and if there's an exception, I can call future.cancel on him and request him to cancel. So I can send him a destructor message and wait for that, or I can actually try to interrupt the very thing he's doing right now. And I have all three of those choices.
Something related to option 2A that I'm sure that you've all thought about, and C++ doesn't even address this now because there's no thread propagation exception propagation between threads at this point.
Mm-hmm.
But what happens in the case of 2A where you've thrown an exception, now you're waiting for the end result, and he throws an exception while all that's going on, and you've added in thread propagation, now you're dead.
So there's a couple of things there. The current C++ rules, without getting deep into it because it's much easier if you have a code example on the board, current C++ rules actually allow you to have multiple active exceptions. They can't be in flight. You can't throw another one while you're propagating one already. But if you have a try-catch, and you catch that one exception, you can do stuff with a throw again and catch it there, right? That's perfectly fine. Right. It's just, if you through something and you're destructing stuff that you can't just automatically have another one come out, right? So I think that may partly address what you're talking about, but I also admit that for that kind of thing you want a whiteboard and code examples to work through.
Using these semantics for the destruction, wouldn't your previous example always force you to wait for both result 2 and result 3 before you can actually exit, in which case you would exceed your...
The reason there is because I was using explicit futures and active blocks, which are, and I've been debating whether if you say active brace, call through brace, whether that should be treated as, a one-shot active object on the stack or one on the heap. And I currently view it as one on the heap. It's just an active and async operation, right? You could take your view as well and put it on.
No, but that would mean that the function would return and the code would still be running.
But
the other option.
But the reason that it's a bit different is because there you're relying on the future. You can always have a future as your handle to the async operation, whether it's an active block or an active method call, member function call. Your future is your handle to it. That's on the stack, but unless you say wait to get the result, you will never block. If you decide, I didn't need to look at it anyway, you just let the future destroy, just throw it away, and you won't block, and you will never be tied to that thing because you never asked for the value.
How would I know that it's not executing still when the function exits?
Oh, but you don't care.
But I have a DLL and I want to be able to unload myself.
Okay, so there's two options. First of all, if you do care, call cancel and ask it to stop. It turns out that much of the time, the person who has the future of int or whatever, if he decides he doesn't care about the int, it doesn't mean that he wants to shoot the asynchronous work in the head. It may be, especially in a local case like that, where you're the guy who owns it. But remember, there could be 5 people waiting for that. Just because you don't care about it doesn't mean other people don't, and still want the result, right? But you can get the semantics you want just by, if it is yours, shoot it in the head, call cancel on the future, which is a way to request a cleanup. So here's a simple example. The white code is the single-threaded code, and the yellow code is what you add to make it concurrent. And I don't claim by a long shot that every piece of code will be this easy to convert, but it's an idea of how this can work. So I have producer-consumer, and you can generalize this, but single producer, single consumer. I fire up, ignore active for now, I fire up a producer I call produce. In a synchronous model, I immediately go in and start executing produce, which goes into this loop. I create a message I call consumer, the global consumer process. I go into it, execute that, so I go and I create and process the messages synchronously, one after the other. When I come back out here, I destroy the producer, then I destroy the global consumer, and I'm done. That's my single-threaded serial mode. Once I put active in front of the class, which says, you can have object, you can make instances of this type active, and on the objects. Now think about the slight difference in what happens. I create an active producer, which means I immediately continue executing here. I've just created conceptually a new thread with a producer. He's going to start running his constructor. I'm going to send him another message, produce, which he might not have done his constructor yet, so it queues up. And then I'm going to send him the destructor message and block. So now producer says, okay, great, I got my constructor, I run my constructor. Oh, look, the next thing is produce. I'm going to execute produce. So now he's going to go in this loop where he gets a message, calls consumer process message, but because consumer is an active object, that's an asynchronous call. It enqueues a message with a copy of, I just lost my mic, that's a signal that I'm taking too long. With a copy of message, and it can spin up as many of these as it can while the consumer takes them and whatever he hasn't processed yet queues up. And then finally, produce ends. So the next thing he gets is the destructor message. So he gets the destructor message, great. Executes that, and then he destroys his thread. The caller now is unblocked. He goes into global shutdown, which calls the destructor for consumer. So it asks the consumer to destroy, but he's already got all the messages in his queue. Maybe he's done half of them. He keeps on doing the messages in his queue by default in FIFO order. I'm getting grins down in the front. Yeah, he wants to write this today. I can tell he wants to go home tonight and write this. So he continues executing his messages. Finally, the destructor message comes up. Oh, great, he executes that, shuts down his thread, goes away. That unblocks the caller, who then exits. Not always that easy, but that's an example of how that can usefully make use of an asynchronous producer or consumer. That's sort of a toy example of how active objects can work.
It's kind of a nitpick, but I guess you use these slides in other talks, so doesn't that loop execute 99 times?
Might be.
What?
And I always have to think about the off by ones. Yeah, 99 times.
Yeah, okay.
So approximately 100 messages. It's 100 for large values of 99. You can insert just arbitrary math jokes. Thank you.
Yeah.
Can you go back to the previous thing? So if the producer constructor goes ahead and creates another active block on the heap, and then you come out again, and then produce is called, and then the object is destroyed. How do you manage object lifetimes in that case?
So you're asking about this line. This creates conceptually, it creates a new object that's conceptually on the stack, but it's got its own thread and its own.
Right. So it goes into the thread and creates another active block on the heap. So then you have.
Oh, if he. So it's not this example. It's if he then made another active block on the heap. Okay.
Exactly. Now if you come out into main again, and then the destructor is called, and then you have you can't manage the object lifetime anymore because there's the other function call that's pending out there. It may have references to the same object.
So these are the kinds of examples we should work through. The short answer to what you just said is yes, you can. Asynchronous operations can launch other asynchronous operations. If they don't wait for them and just let them go and return, you can easily get to the point where you're ready to exit main and you still have outstanding asynchronous operations. That can always happen. Even just new up an active object and let it go and exit, right? That's easy to get into. And so you have to make a decision about does the program ask them to cancel, or does it just wait for them to complete? And wait for complete is the usual case unless you know that certain things need to auto-cancel. And then it turns out you can easily write an auto-cancel template, which on the destructor will call cancel for you on a future. C++ is wonderful.
It conflicts with object lifetimes in the sense it's when you're writing that function, you don't know if you can call within an active block on the stack or not. Right?
Yes. So let's talk just for the last few slides about concurrent collections. OpenMP has many benefits, but it's hardwired to C pretty much. There's not much C++ in it at all. And Fortran, it's coupled onto the language, not in the language. It deals purely in loop context with loops with integer indices. So forget STL. And it doesn't take advantage of the genericity, the rich class types and other things in languages. So here's a little motivation. So my friend David from Cray decided, of course, in his environment, he always would like to see things like for loops, which just do the normal sequential thing. For every x in collection C in a depth first traversal, apply F to that node, that object in the collection. That's serial. What do you want to do it in parallel? Well, for all to the rescue. And so if you've ever seen for all, this is a very common spelling. You say for all x in the do F. There's one other subtle one that we should talk about, and that's ordered for all. Now, imagine that C is a collection that's, say, a tree, like a red-black tree or something, binary tree. So it has some inherent parallelism in it already. Sometimes you just want to traverse it sequentially. Sometimes you want to do depth first and just do everything in parallel. So at each node, immediately fire off asynchronous evaluation of left subtree, asynchronous evaluation of right subtree, asynchronous evaluation of self. Just do everything in parallel all the way down. But sometimes, especially if you're, say, rolling up totals, sometimes you can do the left and right subtrees concurrently, but you then need to wait for them before you can do yourself, right? So that's the ordering. There's an implicit ordering in the traversal, like if you want to bubble up totals or something like that. So the question, do you really need explicit language support for all of these? Or can they be a library? And I thought to myself, well, STL already does collections pretty well. Let's see, what did Alex do? Always ask yourself, what would Alex do? Or Bjarne, right? So, in particular, in STL, you already have this nice separation between collections and algorithms through iterators. So you can write a new collection, and it works with the standard algorithms. It has the right kind of iterator, bidirectional or random or whatever. And you could write a new new algorithm that works with the standard containers, right? Wouldn't it be nice if you could also parameterize the traversal and the concurrency. So in particular, I think this is one that we ought to do anyway in STL, because some, like a set is like a red-black tree, right? It just is. It doesn't say so in the standard, but it just is. There are at least 4 natural traversals of a tree. What are those?
Left first, right first. Is big stuff.
Yeah. So pre-order, post-order, in-order, and our favorite, level order. Right? You go through the level order. At least 4. And what do you do today with std set? You say begin, end. It's in order, but there's no way to get at the pre-order, post-order, level order. So I'm asserting that forget about concurrency. Even without this, you ought to want to be able to do that. Once you can do that, you can also parallelize the kind of concurrency you do. And then you can not only write for each C by depth first traversal, apply F, and then say if you want to do sequential, parallel, or ordered. But you can say breadth first, right? And let those things vary independently. So we already have containers and algorithms orthogonal. We'd like to add 2 more dimensions, the traversal and the concurrency policy. And so in my examples, they'll look very much like STL, except instead of begin-end, there is a range object that knows its begin-end, and you can traverse as a range. It's awful, you know, talk about abstractions. A central abstraction in the STL is the range. You see begin-end everywhere, first, last, begin-end. And they're always separate. There's no range, stood range, so we're fixing that, or at least we're trying to. There's a central abstraction that is just a convention, a discipline. Just take the class Alex. So example uses, I can say for each, this container, depth first order, and here I'm going to use those lambda functions that don't exist yet. But notice it's like an active block without the active. The active is just run asynchronously. You can almost do this in Boost. If you take away the braces and use Boost lambda, if it compiles, you're good. If it doesn't compile, yeah, remember those long nights? Anyway, that's why we need them in the language. So for each of these guys, in parallel, add 42. So I can do that completely in parallel. Or I might say for each of the same collection in order, output it, and by default, that defaults it sequentially. So those are kind of nice things to be able to do. And the one slide, the last slide that shows how does this work, this gives you a sketch. By the way, Andre and policy-based design, how many of you are fairly familiar with policy-based design or have heard Andre talk or his writings? Yeah. You'll love this. Oh, the slide isn't there. Oh. I'm sorry. You can see there's been a cut and paste error by this user. It might be that I'm just really tempting you badly. Let's see. We have a slide which belongs. And you'll get the updated slides when you get this. And there it is. The slide is now there. It's even numbered right. PowerPoint, edit and continue. So take a look under the hood. So the calling code just says algorithm, and then it passes it a range. You say container and traversal, that's the range. You say what you want to do at each step, and then you say you want it ordered, parallel, sequential, whatever. What gets invoked? Well, what this actually resolves to is for each is parameterized. Now instead of begin and end iterators, first, last, it's a range and a function to apply and a concurrency policy. There's that P word. If you see Andre afterwards, is Andre here? No? If you see Andre afterwards, tell him I use the P word a lot. Yeah, probably P. Or ask me to pay him. I pass the range, I reduce the type. I pass the function object, I reduce the type. It could be a pointer or whatever as well. And the concurrency policy. All I do is turn around and say, range, traverse thyself. This is the key point why you want ranges, not arbitrary begin ends. Because the range has to know that it is a range in order to make this work. For instance, in the tree, you have to know where the root is so you can then traverse. It doesn't do you much to start at the begin and the end, right? You can do linear stuff, but you can work around it, but it's much better to have a range. Range, traverse thyself, and I'll pass the function and const, the concurrency policy, and they get deduced again. Inside traverse, it just says, oh, by the way, call the overload that says where to start, which is private, so start at the root. And I'm almost done. Only one function gets executed n times. It's this one, starting with the root. Here's the first time I actually used the concurrency policy. And assuming this weren't a reserved word. I say do this lambda function, this, here I'm passing a chunk of code to execute the concurrency policy. Think of it as just, I can do this in C++ today just with a functor written somewhere else. I'm just writing a functor on the fly. I say do right subtree. So do left subtree, do right subtree. I tell the concurrency policy to do them. I say, by the way, I care about this. If you care about ordering, my natural ordering point is here. Wait if necessary. And then do me, apply func to me. And you can see how this just recursively goes through. And now I just write 3 concurrency policies, each with 2 functions. The sequential concurrency policy, do, just immediately executes the functor it's given and returns. Executes it synchronously. And wait does nothing. Parallel is only slightly more interesting. Do immediately starts active op and returns. So it just immediately launches that. And wait does nothing. And for ordered, which is the one where I can do, say, a couple of things in parallel and then I have to wait at a certain point, do, like parallel, runs active op, so runs them asynchronously. And if you ever say wait, I kept futures to each of these, so I'm going to wait on all the things I've launched so far. And then I continue doing the next thing you tell me. I'm done. We'll see how this generalizes. We'll start with for each, then transform, and then other things. But this is sort of we'll see if it pans out. This is one example of a way to think about concurrency that can bear fruit, might be useful. And I'm sure those of you who are library experts in the room, I know a couple of likely candidates may already be interested in saying, oh, how can I make this work? So here's a way you can do concurrency as a library. See where these things fall in. Active objects, active blocks, futures, rendezvous, these are all about asynchronous agents. Parallel algorithms, all about concurrent collections. And declarative support for locks, transactional memory, all about interactive infrastructure, managing the shared state of memory. So, summary, there's higher level abstractions for today's languages that can be easily mapped to hardware. We never block or re-enter silently by default. We have some isolation boundaries so that we don't need to share, put locks around the stuff in between. And one of the goals is to add declarative support for locks as well. Those are other things I haven't talked about. But there's a snapshot or summary of what the project is about. Here's some other things you can read about. There's the Free Lunches Over article and the Software and the Concurrency Revolution ACMQ article. Both of those are linked on my homepage. And check out the Threads and Memory Model for C++ Working Group page. These are the guys led by Hans Boom who are working on concurrency support for the next C++ standard, including Memory Model and Threads and Locks and Futures API. So it's still Threads and Locks, but we're taking a part step up already, doing futures. And hopefully we'll continue to build from there. And questions?
Yeah, so on the second to last slide, you mentioned how you haven't talked about locks at all. And the 30 or so slides before that, you pretty much made concurrency accessible to the programmer who traditionally been afraid for threading. Are you opening up a can of worms unless you make managing shared state significantly safer?
So, one really good question. The question boils down to, your goal was to make it easy for people to add concurrency to their applications. I am afraid you might have succeeded in that, right?
Unless you make mutable and shared state safer, right?
Exactly, right? That is, well, there's several reasons. One is, well, now they're going to be sharing state. Do they still know how to deal with shared state, which I didn't talk much about other than showing the issues? So definitely transactional memory is something orthogonal to all languages. We definitely, that's our number one big ticket item to deal with that.
So you're not going to release this until you...
Not necessarily. You don't stop the world just waiting for something to happen, right? One of the things that I pointed out here on the second to last slide at the bottom was the bottom part, declarative support for locks. We would be in just such a better place if I could just even say in code, this lock covers these objects, and this lock is at this level of the hierarchy. Because then I can statically and dynamically during testing, compile time and test time, at least figure out if I'm following my own rules. That goes a long way. But yes, we still want transactional.
For example, in your prototypes, have you ever run into a situation where you were reasoning about a particular piece of code and you had to know, is this ever going to be run in active mode or not?
Not too much. Mostly, the only time that really comes up is if you might have a blocking cycle, where you want to make sure you don't have a situation where A waits for B, waits for C, waits for D, waits for A, right? Because that's another way of getting a pretty deadlock without locks, right? Just by message waiting. But in general, that's not as much of a problem. It's a similar kind of thing to locks, but it's easier to reason about in messages, and OpenMPI users and those kinds of people deal with that today. We definitely want to make the world better and safer. But these are abstractions, because I find that the biggest problem people have today, besides locks, is that it's really hard to express concurrency in your application. People use the async result stuff, and it's horrible code that's really hard for you to reason about. People write up threads, and they silently block, and they wonder, well, why is this slow? And you're kind of going on a global lock, and there's nothing in the code to tell you that you're doing it. Your tools can't tell you you're doing it, at least most tools today. So it's hard to express concurrency, and so that's the number one problem to solve. And the next one to solve after that is, okay, now they've expressed lots of concurrency. Now how do we scale that efficiently to the hardware, and how do we make sure they didn't shoot themselves in the foot and give them tooling around debugging, like following messages, step into message, and deadlock and race detection and prevention, that kind of thing.
You kind of touched on this in the answer to that question, but I'd like to address it directly. One of the big challenges of concurrency is not just getting it right, but verifiability, testability. To what extent do you feel like this addresses that?
So there are several things. First of all, one of the most important things that you need to be able to do, and this is point 4 in the project goals there, is to be able to let people express concurrency in a way they can reason about. And just having bulk threads where they can block arbitrarily, re-enter. I mean, if you've ever used COM-STA, single-threaded compartments, you've learned the nightmares involved with that. So anything that gives you a level of abstraction, like active objects, futures, and messages, that you can see in your code what's going on, who's waiting for what, and that makes things more explicit. So you can express almost everything you could at the lower level, but with a higher level of abstractions, there are guardrails to prevent you from driving off the cliff. It's just like you can write your own virtual function tables, your vtables, in C. But if you use C++ virtual functions, you can do almost everything you could at the C level, except the dangerous stuff, most of it. Right? And so it gives you a higher level to think at, and so you have a better chance of reasoning that your program is correct.
Yeah, I mean, you're certainly preaching to the choir in terms of higher levels of abstraction, expressiveness, but one of the real challenges of testing concurrent applications is the non-determinism involved. Mm-hmm. I don't hear anything about that.
So one of the things I called out was that there's a lot of tools issues, really at the language level. This affects everything from hardware, OS, runtimes, languages, tools, applications. And I wanted to give that context because there's more than just the language level. Much as us language guys would love to think that we're the most important people in the world, well, we're not. So tools, you need better debugging tools, profiling tools to see where you're losing concurrency. You need to be able to reason about the state of your program. You need code coverage takes on a whole new meaning because one of the things you point out is code coverage ain't enough anymore. Is what are all the interleavings? In particular, one big one that gets you a lot of the way out of the hole that you're concerned about, which is a very valid hole, is if we had perfect race detection tools, which by the way aren't known today, but imagine if we had perfect race detection tools so that you could at test time prove that your code, at least modulo any plugins that you don't know about yet, that you have no races in your code, you are correctly locked, and that you are deadlock free. Wow, that just gives you 1,000% better position to be in knowing that your code will actually run correctly. So there are no perfect race detection tools and deadlock detection tools today. There are, however, ones that are in practice or that are in research that I know about that are in the high 90s%, which gets you much further than the 0 that we're at right now. So those are the kinds of tools that need to help more. It's not going to be a perfect world. You're not going to be able to say tomorrow, oh, I know I'm race and deadlock free. But the closer we can get you to being able to say that at test time, rather than at customer calls you from the customer site time, is a win.
Thank you.
Kurt, by your own admission, active objects...
I love the way that sounds. Let me hide behind it.
Active objects and message passing don't save you from deadlock, right? But
It doesn't save you from blocking cycles.
Right.
You don't need to lock the internals, which removes a fair amount of some of the blocking you would otherwise be doing.
I've heard you assert a couple of times that less of an issue for message passing and active objects than it is for lock-based code. What justification do you have for that?
That's a really good question, and there's several aspects of the answer. One is that messages tend to be more explicit. They also tend to be more debuggable and toolable because of the abstraction they represent. Waiting for a message is more than waiting for a locked on block. There's more semantic content for tools to help you with, and it's easier for you to reason about. For example, if you're going to, it gives you more to reason about. Let me go to a second thing. The second thing is you can do more with a message to prevent a cycle than you can do with a lock. In particular, if you're waiting for a message to receive and you know you can be part of a blocking cycle, but you don't actually need to block for this message, you know what needs doing, but it doesn't have to happen synchronously, you can, like I showed in that one line of code example, fire up an active block that says, wait for this future and do this. And now you've broken the cycle. You cannot do that with an unlock, which must happen on the same thread that got the block. So those are two examples, one sort of qualitative, one more specific. You have a better abstraction you can reason about, plus you can do more stuff with messages. You can do stuff you can't do with traditional locks. Unless you go into some locking systems that let you acquire on one and release on another, but most real-world systems aren't like that. If that helps? What about semaphores? Semaphores down at the assembler level of concurrency? Yeah, so a lot of these higher level things are built on such things. And it turns out that most of the time when people reach for a semaphore, they should be reaching for something from a higher shelf.
You, in your examples, showed active being tagged on both the class and the object instance level. What is it that the active semantic requires that it must be at the class level? And second part, what is the cost of that on the class level when you don't use it on the instance level?
Good questions. So the answer to the second part is 0. The answer to the first part, and this will make it explain it a bit better. I would love to be in a world where I can just say active T, little t, for any type T. You can't do that. It is not safe to treat any old existing C++ type and as an active object. Think of what you could do. You might imagine, okay, for any type, any class you might have written in your long career, 20 years ago you dusted off, create an active object of that, which now runs on its own thread. The constructor is a message. I can build all that around it and force it into that little box. I can even automatically, in the compiler, change its return value from int, from its member functions, to future events. I can do that kind of thing automatically. The out parameters are a bit harder, but I can still do those too. However, what if you're a vector? Imagine an active stood vector. This is a killer example. I create an active stood vector, I insert and I push back something, I access the 0th element. What does it do? It returns me a reference into the object. Now I've got shared state. Now I've leaked the internal representation of the object, and it's no longer isolated. So the question arises, okay, active objects could be a nice abstraction. Not safe to do with every kind of object. There are certain things you must not do, which I described, in particular, leak pointers or references to your internal state. So by putting active on the class, that's just a tag for this could be instantiated active or not. It could be just a normal object. But as soon as you say that, that's intended to be the tag for, now I'm turning on extra checks. I do not allow you to expose addresses of members and stuff like that. You have to have some discipline because C++ will let you do all sorts of stuff, hide pointers, places, and sneak them out in other ways. But it gives you a tag that, okay, I intend to turn on a set of warnings or some restrictions for this class so that it is intended to be safe to use as an active instance or as a non-active passive instance.
Would those particular challenges be mitigated by a better memory model for C++ that uses atomic memory operations and protects you from that sort of challenge?
Not specifically. All of this stuff, you need a memory model as a foundational piece. It doesn't, that part isn't really effective. You need that anyway, and it doesn't really affect what you get there. Because the issue is like pointer aliasing. You're creating aliases, and the memory model just says how you may do that, not when you may.
If you take this this whole idea and pull it back to the first part of your talk, I see that there's a basic problem in that when you have 256 processors, your average programmer is still not going to be able to design, to figure out how to parallelize that the thing. And this is, do you have any thoughts on this whole idea?
So, there's a couple of things. Let me lay it out in 2 or 3 steps. The first thing is, when you talk about concurrency, responsiveness and throughput are 2 different things. You got to deal with both of them. It's throughput that's going to make your 256 processors sing and dance and actually use them. Being able to run things asynchronously is important for responsiveness and for some level of using up processors. You know, you were talking like 1632, 64. We're not talking like 256 or 1000, right? It's been fairly adequately shown, even though so far most of our parallel computing experience is in scientific engineering, as somebody has jobs for it. Right? You don't, of course. That data parallel is where you really get the bang for the buck to go to your 1000 processor machines like Crays and Tera machines. So to the extent that we're putting a Cray in everybody's knapsack over the next decade or 2, where you're really harnessing the full throughput issues from current collections, and so having people be able to take their collections, write for each parallel or for each order or something like that as a traversal, or something like OpenMP if you want to cobble it together at a bit of a lower level with more restrictions and less safety. That's really where the big bang for the buck is going to come from. So it's not a perfect world. Let me just point out the major issue with that. When you call for each, like I just showed in those wonderful examples, and you pass it this predicate named F, just do this to every node. So, among other things, you have to know that there are no side effects. There is no way to declare in most imperative languages today that a given functor or operation is free of side effects. If there are side effects, you are hosed, that you are so hosed. The good news is that on a 1000 processor machine, you will be hosed so much faster. This is good. You'll be hosed so much faster, and because you will get a test time every time. And I was talking with David a year ago, and I was bemoaning last Christmas about how this is awful, how the 4 and 8 core machines are going to be exposing more and more concurrency bugs in our shipped code, like everybody's, the whole industry, that are just waiting for actual hardware parallelism to manifest. They're just gleefully waiting, those little bugs, right? Bugs. That's not even the line word. And so he just smiled and said, you know, that really wasn't much of a problem for us. We ran on 1000 processor machines. If there was a race in it, it fell over right away. Oh, you know, that could actually be a feature. It wasn't always that way. But it does, because we're at the beginning of this curve now, we're actually at a more painful point. So when sometimes it seems the pain is too much to bear, just remember, it's going to get better, the tools will get better, you'll be able to harness the power more in more effective ways, and be able to get into a better place. But this is sort of the pain point as the industry goes through this evolution and the birth, just as we went through the birthing of OO and of other things.
So, just to make it a little clearer for myself, adding active, which looks pretty innocent, to a piece of code can break it.
Adding active to a piece of code could break it. What do you have in mind?
I don't know if it uses shared state somewhere.
Yeah. Sorry, when you say adding active, do you mean adding like an active block, run this piece of code active, or do you mean adding active to an object?
To a piece of code that is going to do some stuff.
So you definitely can break. You need to know what you're doing. For example, the most obvious thing is, if I have this function, 100 lines, and I want to put 20 of them into an active block, they better not assume they're running under the locks held by the function. Like, they better really be independent of what I'm doing in this function. If they assume they're under the lock, and now they start doing work outside the lock, that's not good.
Yeah. Alternatively, you could have, say, a function that in a library that in your application is never called actively, and somebody else is actually using it actively. Now you could add a piece of code to that function that now breaks it for another person.
Okay, so the question is, any arbitrary piece of code could now be called active or not active. That's true. Any arbitrary piece of code can today be called by somebody spinning up a thread and passing it to a big line that executes.
The big difference being that spinning up a thread is really hard, so few people do it. But here's my worry: is that the first thing I want to do if this comes out is like tell my entire team, yeah, it's awesome, but you're not allowed to use it. Only the 2 people that know the entire architecture of my system and know all what's going on are allowed to use it.
So there is some merit to what you say. You are like C++ and higher level languages have always done, and systems languages, unlike some toy languages, you can abuse features. There's no question about it. Having said that, one of the interesting things is people said exactly the same thing about objects
Well, don't
and
get me
garbage
wrong, I
collection.
think it's awesome. I
50
want it to
no,
stop.
but it's worth, this is actually a good point I didn't make earlier, so after this I'll take one more question and we'll wrap up. But people said exactly the same thing about objects and about garbage collection. So how many of you were in this industry in the early 1990s? Okay, of those with their hands up, keep your hand up if you attended conferences, software conferences in the early 90s. Okay, how many of you, who still have your hands up, went to talks with breathtaking titles like, what is an object and what is a virtual function? Some. When this was all new, I mean, there were gurus whose whole claim to guruhood was they knew what an object was, right? It is not rocket science anymore. People know what an object is, its state, and the operations that work on it, bundled together, encapsulation, blah, 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 as Steve Ballmer would say. And we know this now, but this was not common knowledge. This was considered too hard for most people back in the day.
A different thing though,
And
the objection,
for the next, let me just finish the thought.
Yeah, sure.
And for the next 5 years or more, and this has already begun, I know because I've given these talks, is people will go to talks with breathtaking topics like, what is an active object? What is a future? What is a message? And so there's some education as to what the abstraction is and how to use it.
The common objection back then was performance. Right now, the objection would be correctness.
I think the objection then, as I remember, was also correctness. People don't understand what a virtual function is. Look, this deep virtual function call in a constructor isn't actually deep in C++, or conversely, it is deep in Java. And look how people can shoot themselves in the foot. And they're accessing uninitialized state, right?
Yeah, true that.
People have to learn how to use it. Most people don't object to the, today at least, to the complexity argument, even though it's still true, right? Somebody basically is, over the next 5 years, I guarantee you, I don't know if his name is Scott, is going to write effective concurrency, right? One more. Yes.
Concurrency, you're right.
If we use lambda expression in the what we might want to separate snapshots of variable from dynamic linked variables. Because what happens, this function, lambda expression, will not be executed immediately.
Yeah.
So variable could change. So if you can create construction which separates snapshots.
Can you come to Portland next month to our ISO C++ meeting? I tell you. So the question is, so you have a lambda function. You pass variables in. Well, because you're basically writing a functor on the fly and passing in variables implicitly. Like if you reference a variable in an outer scope, you're implicitly passing them. And the $64,000 question is, by value or by reference, right? There was extended discussion in Berlin this April at our last ISO C++ meeting when we were discussing the two memory model proposals. About 2/3 of the people in the room thought that it should be by reference, and I was one of the few who said, no, 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 it's got to be by value because you're going to, concurrency people will kill you if you implicitly create aliasing. And actually, I think the answer is somewhere in between, because sometimes by reference is okay, but the danger of by reference is that you're now creating aliasing, right? But you want it for large structures. You do not want to copy your million element vector. So there's got to be a clear way. And one of the proposals, for instance, decorated their lambda with ref paren x paren, like if you wanted to pass a reference. And maybe something like that will fly. We're still working on it. But you have hit on the question in the competing proposals for lambda functions.
Actually, if you pass by reference, you can create another wrapper which creates explicit looking routing. So then this passed by reference from different lambda can be just locked on the size.
Yes. So there are definitely reasons to use each. I worry gravely if a silent pass by reference is the default, that people will just write without realizing they're writing it, because they're creating, as soon as they do that, it's implicitly creating a shared, mutable shared state that you've got to know to lock. And so it's the wrong default, but there's got to be a way to do it. So
I think explicit syntax construction is the way to do it. Just explicitly say this is by value or by reference.
Yeah. And then people, so currently the way I think that, I could be wrong, but the way I think that one's going to end up, because there are good arguments not to default to reference, by reference, but there are also good arguments not to default to by value. I happen to like these arguments more, but there are people who like these arguments more. I think the most likely outcome at this point, I could be wrong, is that there will be no default, and you have to say explicitly for each one. I don't think that's necessarily the best answer, but it's a possible answer. So. Yeah, you can come to Portland too. Anybody who wants to argue against defaulting to by reference, Portland, October 15th to 20th, be there, be square. With that, thank you very much for taking the time, and I hope this has been useful for you.